A black hole is a region in space where gravity is so strong that nothing can escape it, not even light. Imagine a place where the pull of gravity becomes so powerful that once something crosses a certain point, it cannot come back. This point is called the event horizon. It acts like a boundary. Once an object passes this boundary, it disappears from view, because even light, the fastest thing in the universe, cannot move fast enough to get away. Without light escaping, a black hole looks completely dark, which is how it got its name. Gravity is a force that pulls objects toward one another. On Earth, gravity keeps us on the ground. The more mass an object has, the stronger a black hole forms when a huge amount of mass gets squeezed into a very small space. Think about a star that is many times heavier than our Sunday. When it reaches the end of its life, it collapses under its own weight. If the star is massive enough, it keeps collapsing until all of its mass is packed into a point that is smaller than you can imagine. This point is called a singularity. At the singularity, density becomes infinite, and the laws of physics as we know them no longer work. Consider the Sunday for a moment. It has a strong gravitational pull. If you replace the Sunday with a black hole of the same mass, Earth and the other planets would continue to orbit in the same way. They would not get pulled in. This is because gravity at a distance works the same. The difference comes when you get very close to the black hole. As you move closer, gravity increases rapidly. Near the event horizon, the pull becomes so intense that escape becomes impossible. Black holes come in different sizes. Some are small, with a mass a few times greater than the Sunday. These are called stellar black holes and form when massive stars die. There are also supermassive black holes, which are millions or even billions of times heavier than the Sunday. These giant black holes sit at the centers of galaxies, including our own Milky Way. Scientists think supermassive black holes may play an important role in the way galaxies form and grow. To picture how a black hole bends space, imagine a stretched sheet of rubber. Place a heavy ball in the middle of the sheet. The sheet curves around the ball, and smaller objects placed nearby roll toward it. The ball represents a massive object like a star. Now, imagine that the ball is so heavy, it makes a deep well in the sheet. At some point, the well becomes so steep that nothing can climb back out. That is similar to what happens near a black hole, except space itself is bending, not a rubber sheet. If someone fell into a black hole, their experience would be strange and extreme. As they approached the event horizon, time would seem to slow down for them, when viewed by someone watching from a safe distance. To the outside observer, the falling person would appear to move slower and slower until they seemed frozen at the edge of the event horizon. However, from the point of view of the person falling, time would seem normal. As they got closer, the difference in gravity between their head and feet would stretch them out. Scientists call this process spaghettification, because it would stretch a person into a long, thin shape like spaghetti. This happens because gravity at the feet is much stronger than at the head, pulling harder on the lower part of the body. We cannot see black holes directly because no light escapes. Instead, scientists detect them by observing their effects on nearby matter. For example, if a black hole pulls gas or dust toward it, the material swirls around and heats up as it falls inward. This heated matter can glow brightly in X-rays, which telescopes in space can detect. Another clue comes from watching the movement of stars near a black hole. If a star orbits an invisible object with great speed, it suggests that something very massive is there. This is how scientists discovered the supermassive black hole at the center of the Milky Way. Black holes are not cosmic vacuum cleaners sucking up everything around them. They only capture objects that come too close. If you stay far away, you are safe. Space is so vast that most black holes are harmless to us. Even the nearest black hole to Earth is far enough away that it poses no danger. When two black holes collide, they create ripples in space called gravitational waves. These waves travel outward, like ripples on a pond after a stone is dropped. In 2015, scientists detected gravitational waves for the first time using very sensitive instruments. This discovery confirmed an important prediction made by Albert Einstein more than a century ago. By studying these waves, scientists can learn more about black holes and the events that create them. The idea of a black hole may sound like science fiction, but there is strong evidence for their existence. Telescopes have captured images of the shadow of a black hole by observing the light bending around it. In 2019, scientists released the first picture of a black hole in a galaxy called M87. The image showed a dark circle surrounded by a glowing ring of hot gas. This was a major milestone in astronomy and gave us a direct view of something that had only been imagined before. Black holes challenge our understanding of space and time. They show us that the universe has extremes beyond our daily experience. They are places where the known laws of physics break down, and new theories are needed to explain what happens inside. Scientists continue to study black holes to answer questions about how they form, how they grow, and what happens at their very center. Imagine standing on the edge of a cliff, looking into a dark void so deep that you cannot see the bottom. That feeling of mystery and danger captures what a black hole represents on a cosmic scale. These regions of space are hidden, powerful, and fascinating. They remind us that the universe is full of places we have yet to explore and understand. The largest black holes in the universe are called supermassive black holes. These giants have masses millions or even billions of times greater than the Sunday. To imagine how massive they are, picture a single grain of sand representing the Sunday. A supermassive black hole would then be like a mountain towering over that tiny grain. Despite their size, they are still invisible because their gravity is so strong that not even light can escape. What we see instead is their effect on nearby stars, gas, and dust. Supermassive black holes sit at the centers of most large galaxies. The Milky Way, our galaxy, has one of these black holes at its heart. It is called Sagittarius A, and it has a mass about 4 million times greater than the Sunday. Even with that incredible mass, it is still far away from Earth, about 26,000 light-years. A light-year is the distance light travels in 1 year, which is nearly 6 trillion miles. This means Sagittarius A is so far away that its gravity has no direct. The stars near the center of the Milky Way, however, move at high speeds, because they are under its powerful influence. The origins of supermassive black holes remain a mystery. Scientists know how smaller black holes form. When a massive star runs out of fuel, it collapses under its own gravity and becomes a black hole. This process creates stellar black holes, which are a few times the mass of the Sunday. But this process cannot explain how supermassive black holes reached their enormous size. Some scientists think these giants began as smaller black holes that grew over billions of years by pulling in gas, dust, stars, and even other black holes. Others suggest they may have formed very early in the history of the universe, perhaps from huge clouds of gas collapsing directly into black holes without forming stars first. Both ideas are still under study. To picture how a supermassive black hole feeds, imagine water swirling down a drain. When matter falls toward a black hole, it spirals inward and forms a flat disk called an accretion disk. As the material in the disk moves closer to the black hole, it rubs together and heats up. This heat produces intense light and radiation. In some cases, the energy released can be brighter than all the stars in the surrounding galaxy combined. These bright regions are called active galactic nuclei. When the activity is especially strong, they are called quasars. Quasars are so bright that we can see them from billions of light years away, showing us how powerful these objects can be. The Milky Way's central black hole is quiet compared to a quasar. It is not actively feeding on large amounts of material right now. If a large cloud of gas were to fall toward it, the area around Sagittarius A would flare up and shine brightly in X-rays and other forms of light. Telescopes in space would be able to detect this change. Observing these flares helps scientists understand how black holes behave and how they interact with their surroundings. Scientists know supermassive black holes are present because of the way stars move near them. In the 1990s, astronomers used powerful telescopes to track stars at the center of the Milky Way. They saw stars whipping around an invisible point at incredible speeds. By measuring these movements, they could calculate the mass of the object causing them. The only explanation was a supermassive black hole. Later, in 2022, astronomers used a network of radio telescopes around the world to capture the first image of Sagittarius A. The picture showed a dark center surrounded by a glowing ring of hot gas. It confirmed what had been suspected for decades. Supermassive black holes do more than just sit quietly at the centers of galaxies. They can shape the galaxies around them. When a black hole feeds on matter, it can release powerful jets of energy that shoot out into space at nearly the speed of light. These jets can travel thousands of light years, heating up or blowing away nearby gas. This process can slow or even stop the formation of new stars. In this way, black holes help control how galaxies grow and change over time. Without them, consider two galaxies on a collision course. As they draw closer, their stars and gas clouds interact and mix. At the heart of each galaxy sits a supermassive black hole. When the galaxies finally merge, their black holes may spiral toward each other and eventually collide. This event would release a burst of gravitational waves, ripples in the fabric of space. In 2015, scientists detected gravitational waves for the first time. These waves came from the collision of two smaller black holes. Detecting waves from merging supermassive black holes would give us even more information about how these giants evolve. Supermassive black holes are not dangerous unless you get very close to them. Even if our solar system were much nearer to Sagittarius A, we would not be sucked in unless we crossed the event horizon. The event horizon is the boundary around a black hole where escape becomes impossible. Outside of this boundary, objects can still move freely, though they feel the black hole's pull. This is why stars near the center of the Milky Way can orbit safely without falling in. Imagine standing far from a campfire. You can feel its warmth, but it is not enough to burn you. As you step closer, the heat becomes stronger. If you step too close, you cannot avoid getting burned. A black hole works in a similar way from far away. It has no direct effect. As you move closer, its gravity grows stronger, until at the event horizon, there is no way back. Near the event horizon, gravity becomes so extreme that time slows down compared to regions farther away. If you watched someone falling into a black hole, they would appear to move slower and slower until they seemed frozen at the edge. From their point of view, though, time would feel normal as they crossed the boundary. This strange effect comes from the rules of general relativity, a theory proposed by Albert Einstein. Studying supermassive black holes is difficult because they are so far away and hidden behind clouds of gas and dust. Astronomers use different types of telescopes to gather information. Radio telescopes can see through dust and reveal the structure of jets and disks. X-ray telescopes can detect the high-energy light produced by hot material falling into black holes. By combining data from many telescopes, scientists can create a clearer picture of these mysterious objects. The story of supermassive black holes is also the story of the universe itself. These giants have been part of galaxies for billions of years. Their growth and activity are tied to the birth and death of stars, the movement of gas, and the overall shape of galaxies. By learning more about them, we gain insight into how the universe works on its largest scales. Even though they are hidden, their presence is felt across vast distances. They are silent engines that drive the evolution of the cosmos, shaping the places where stars and planets, and even life, can exist. Black holes are invisible by nature because no light can escape them. Light is what lets us see objects in space, just like it helps us see things around us on Earth. When you look at the moon, you are really seeing sunlight reflecting off its surface. Stars shine because they produce their own light. Even planets are visible because they reflect light from their star. Its gravity is so strong that once light crosses a certain point, called the event horizon, it cannot escape. Without light coming out, there is nothing for a telescope to capture directly. To us, it appears as a completely dark, empty spot in space. Since black holes cannot be seen directly, scientists study the way they affect the things around them. This is similar to figuring out the shape of the wind by watching how it moves leaves or grass. You cannot see the wind itself, but you can see its effects. In the same way, a black hole reveals itself by how it influences nearby matter, such as gas, dust, or stars. One of the most common ways to detect a black hole is by looking at material that is falling toward it. Imagine water swirling down a drain. The closer the water gets to the drain, the faster it spins, and the more energy it releases. When gas and dust spiral toward a black hole, they form a thin, flat structure called an accretion disk. Friction between particles in the disk creates intense heat. This heat makes the material glow, but not in ordinary light that we can see with our eyes. Instead, it shines in X-rays and other high-energy forms of radiation. Space telescopes equipped to detect X-rays can pick up this signal, showing us where a black hole is actively feeding. The black hole itself stays dark, but the surrounding material can be incredibly bright. An example of this can be seen in systems where a black hole has a companion star. The star orbits the black hole, and sometimes the black hole pulls gas away from the star's outer layers. As the gas falls in, it forms an accretion disk that glows in X-rays. By studying the pattern of these X-rays, astronomers can learn about the black hole's mass, spin, and other properties. One well-known case is Cygnus X-1, a black hole located about 6,000 light-years from Earth. Scientists discovered it because of its strong X-ray emissions, which come from the matter it is pulling from its nearby star. Another clue to a black hole's presence comes from observing the motion of stars. At the center of our galaxy, the Milky Way astronomers have tracked stars moving in tight orbits around an invisible object. These stars move at incredible speeds, some traveling thousands of miles per second. The only explanation for this behavior is a massive object with an intense gravitational pull. By measuring the star's movements, scientists calculated that this hidden object must have a mass millions of times greater than the Sun. This led to the discovery of Sagittarius A, the supermassive black hole at the heart of our galaxy. No telescope can see Sagittarius A directly, but its existence is clear from the way it controls the motion of nearby stars. Black holes can also reveal themselves through dramatic events, such as when they tear apart a star. If a star wanders too close to a black hole, the difference in gravity between its near side and far side stretches it apart in a process known as tidal disruption. The star gets ripped into streams of gas, which spiral into the black hole. As this happens, the gas heats up and produces a sudden burst of light. Telescopes can detect these bright flares, which are evidence of a black hole at work. These events are rare, but provide valuable information about how black holes interact with their surroundings. In 2015, scientists discovered another way to detect black holes: gravitational waves. These are ripples in space itself, created when massive objects like black holes collide. Imagine throwing two stones into a pond at the same time. The ripples spread out from each stone and eventually meet, creating a complex pattern on the water's surface. Gravitational waves behave in a similar way, except they move through space rather than water. Sensitive detectors on Earth, such as LIGO, can measure these tiny ripples. The first detection came from the merger of two black holes billions of light years away. Even though the black holes themselves were invisible, their collision sent out a signal strong enough for us to detect. This breakthrough gave scientists a new way to study black holes without relying on light at all. Sometimes black holes create powerful jets of particles that shoot out at nearly the speed of light. These jets do not come from inside the black hole itself. Instead, they form when material in the accretion disk interacts with magnetic fields and gets flung outward. These jets can stretch for thousands of light years and shine brightly in radio waves and other types of radiation. By mapping these jets, astronomers can trace them back to the area around a black hole. Even though the black hole remains hidden, the jets act like a signpost pointing to its location. To understand why black holes stay invisible, consider a familiar example on Earth. If you drop a ball into a deep well and shine a flashlight after it, you can see the ball because the light travels back to your eyes. Now imagine a well so deep that once the ball passes a certain point, even light cannot climb back out. No matter how bright your flashlight is, you will never see the ball again. This is similar to what happens at a black hole's event horizon. Once light crosses this boundary, it is trapped forever. Since light is our main tool for seeing, the black hole becomes hidden. The first direct image of a black hole was captured in 2019 by a project called the Event Horizon Telescope. Scientists linked radio telescopes around the world to create a planet-sized array. They focused on the supermassive black hole in the galaxy M87, about 55 million light-years away. The image showed a dark center surrounded by a glowing ring of light. The dark center was the shadow of the black hole caused by light bending and swirling around the event horizon. Even in this image, the black hole itself remained unseen. What we saw was the glowing matter around it, giving us indirect proof of its presence. Black holes challenge our understanding because they hide behind a cloak of darkness. Everything we know about them comes from the way they shape the space and matter around them. By watching stars speed around an unseen center, by detecting bursts of X-rays from hot gas, by measuring gravitational waves from distant mergers, or by tracing giant jets across space, we slowly piece together their story. They are cosmic puzzles that we solve not by looking at the pieces directly, but by studying the spaces between them and the patterns they leave behind. Even though we cannot see black holes with our eyes, their influence stretches across the universe, making the invisible unmistakable. Some black holes are so massive that they defy our imagination. Theoretical predictions suggest that the largest of these, sometimes called ultramassive or cosmic titans, could reach tens of billions of times the mass of our Sunday. These giants sit at the very edge of what we believe is possible in the universe. To understand their scale, imagine the Sunday as a single grain of sand. A black hole with billions of solar masses would be like a mountain made of sand towering above you, so vast that it seems endless. Even though these black holes are invisible, their effect on their surroundings is so great that entire galaxies can revolve around them. Supermassive black holes, like the one at the center of our galaxy, already contain millions or billions of solar masses. A black hole as large as a few billion solar masses can hold an entire galaxy in its grip. But there may be some that grow even larger. These theoretical titans are thought to form in regions of space where matter is especially dense. They could start as smaller black holes that grow over billions of years by pulling in gas, dust, stars, and even other black holes. Each time two galaxies merge, their central black holes may move toward each other, spiral closer, and eventually combine. This process could repeat over cosmic time, creating larger and larger black holes. In theory, this cycle could produce a single black hole with a mass of tens of billions of suns. To picture how such growth happens, imagine a city where buildings keep merging into taller structures. At first, the city has many separate buildings of different sizes. Over time, the buildings combine into massive towers. In the same way, galaxies collide and merge, feeding the black hole at the center with more material. With each merger, the black hole gains more mass, just as the tower gains more height and bulk. Over billions of years, what was once an ordinary black hole could become a cosmic titan. Astronomers have already found evidence of black holes that approach this scale. One example is the black hole in the galaxy home, 15A, which has a mass estimated at around 40 billion suns. This galaxy sits at the center of a large cluster of galaxies. Its central black hole likely reached this incredible size by consuming smaller black holes and enormous amounts of gas during multiple galactic mergers. Another example is TUN 618, a distant quasar powered by a black hole thought to weigh more than 60 billion solar masses. At such a distance, we are looking at light that left the quasar billions of years ago, giving us a glimpse into the early universe. These black holes are rare, but they show us that growth to extreme sizes is possible. They help explain how some galaxies became so massive and bright. When a black hole feeds actively, the gas and dust falling into it form a structure called an accretion disk. Friction in the disk heats the material until it glows with intense light. This energy can outshine all the stars in the surrounding galaxy, making the region known as a quasar. Quasars are among the brightest objects in the universe, and they are visible across billions of light years. The energy released by a quasar comes from matter falling into the black hole, a process that turns gravitational energy into radiation. A cosmic titan black hole can drive a quasar so powerful that it lights up the early universe like a beacon. Even though these black holes are extremely massive, they do not act like cosmic vacuum cleaners sucking in everything nearby. Their gravity, while immense, works like gravity everywhere else. The strength of their pull depends on distance. For example, if our Sunday were replaced by a black hole of the same mass, Earth would continue to orbit as usual. It would be dark and cold, but it would not get pulled in. The same is true for a galaxy around a cosmic titan. Stars far from the center continue to orbit normally. Only objects that come very close are at risk of crossing the event horizon, the point where escape becomes impossible. The sheer size of these black holes affects the structure of their galaxies. When a black hole grows to extreme mass, it can influence how gas moves and where new stars form. In some cases, powerful jets of particles erupt from the region around the black hole. These jets travel at nearly the speed of light and can stretch across thousands of light years. They heat the surrounding gas and may prevent it from cooling and forming new stars. In this way, a cosmic titan black hole can control the growth of its entire galaxy, acting like a central engine that regulates star formation. Scientists are still trying to understand how black holes can grow to such extraordinary sizes. One possibility is that they began forming very early in the universe before galaxies had fully developed. In this scenario, massive clouds of gas could have collapsed directly into black holes without forming stars first. Starting with a larger seed would make it easier for the black hole to reach a final mass of billions of suns. Another idea is that these black holes simply had more time and material to grow. In the dense centers of galaxy clusters, there is plenty of gas and many smaller black holes available to merge. Over billions of years, this constant feeding could create a cosmic titan. Detecting these giant black holes is challenging because they are so far away and hidden by thick layers of dust and gas. Astronomers rely on indirect clues. One method involves observing the motion of stars near the galactic center. If stars move at very high speeds around an invisible point, it suggests a black hole is present. The faster the stars move, the more massive the black hole must be. Another method uses the light from the accretion disk. By studying the brightness and energy of the light, scientists can estimate how much material the black hole is consuming and how massive it might be. In recent years, advanced telescopes have begun to capture clearer images of these regions. In 2019, the Event Horizon Telescope produced the first image of a black hole's shadow. This historic picture showed the supermassive black hole in the galaxy M87, which has a mass of about 6.5 billion suns. While this is not yet at the level of a cosmic titan, it demonstrates that imaging techniques can reveal details once thought impossible to see. Future projects may allow us to study even larger and more distant black holes directly. Gravitational waves provide another tool for detecting cosmic titans. When two massive black holes merge, they create ripples in space itself. These waves travel across the universe and can be detected by sensitive instruments on Earth. So far, we have observed gravitational waves from smaller black hole mergers. Detecting waves from the merger of two cosmic titans would be a groundbreaking discovery, offering direct evidence of these extreme objects and how they grow. The idea of a black hole with tens of billions of solar masses stretches our understanding of physics and astronomy. It raises questions about how matter behaves under extreme conditions and how the largest structures in the universe form. These titans are not only fascinating objects in their own right, but also keys to understanding the history of galaxies and the evolution of the cosmos. They remind us that the universe operates on scales far beyond human experience, with forces and events so vast that they challenge the limits of our imagination. The event horizon of a black hole is the boundary where escape becomes impossible. It is often called the point of no return. Once anything crosses this invisible line, it cannot get back out, not even light. The size of the event horizon depends on the mass of the black hole. The more massive the black hole, the larger its event horizon. For the biggest black holes, this boundary can be staggeringly large, stretching farther than the entire solar system. To understand how large this is, think about the distance from the Sunday to Neptune, the farthest major planet in our solar system. That distance is about 2.8 billion miles. Our solar system is already vast, with space between planets so great that light itself. Now imagine a single black hole so massive that its event horizon is larger than all that distance combined. If you place this black hole at the center of our solar system, its boundary would reach past Neptune and possibly even beyond the orbit of the dwarf planet Pluto. Everything inside that area would be trapped, unable to escape its pull. The event horizon does not have a physical surface. There is nothing solid there. No wall or barrier to touch. It is simply the point at which space and gravity are bent so extremely that nothing can move fast enough to break free. If you were floating toward a black hole, you could pass across the event horizon without feeling it. You would not notice a change in texture or temperature at that exact spot. The difference is that from that moment onward, no force or engine, no matter how powerful, could get you back out. The size of an event horizon is described by a measure called the Schwarzschild radius. This is the distance from the black hole's center to the event horizon. For a black hole with the mass of our Sunday, the Schwarzschild radius would be about 3 kilometers, or just under 2 miles. That is very small compared to the Sunday's actual size, which has a diameter of nearly 865,000 miles. This shows how incredibly compact a black hole is, but when you increase the mass, the Schwarzschild radius grows in direct proportion. A black hole with a mass of millions or billions of suns has an event horizon large enough to engulf entire planetary systems. For example, the supermassive black hole at the center of our Milky Way, called Sagittarius A, has a mass about 4 million times that of the Sunday. Its event horizon would be roughly 7.3 million miles across. To compare, the distance from the Sunday to Mercury is about 36 million miles. This means the entire event horizon of Sagittarius A would fit well inside Mercury's orbit, making it enormous by human standards, but still relatively small compared to the scale of our solar system. However, some black holes are far more massive than Sagittarius A. Astronomers have discovered black holes weighing tens of billions of solar masses. For one of these cosmic giants, the event horizon could be more than 100 billion miles across. At that scale, it would easily extend past the orbit of Pluto and well into the outer regions of the Kuiper Belt, a zone filled with icy bodies at the edge of our solar system. If such a black hole were placed where our Sunday is, the Earth, the other planets, and even distant dwarf planets would all fall well inside its point of no return. Imagine standing on a hill, looking at a deep valley filled with fog. You cannot see the bottom, but you know it drops far below where you stand. The event horizon is like the edge of that fog-covered valley. You can move toward it and even cross into it without feeling an exact point where the ground changes. But once you cross, there is no way to climb back out. This image helps explain why black holes are so hard to study. From the outside, you can only observe the effects on nearby matter. The event horizon hides whatever happens inside. The idea of something that large can be hard to picture. To make it more relatable, think of a black hole's event horizon as a bubble surrounding the black hole. This bubble represents the boundary of no return. For a stellar black hole with a mass about 10 times that of the Sunday, the bubble would be only about 30 kilometers wide. You could drive around it in less than an hour. For a black hole like Sagittarius A, the bubble would be millions of miles wide, large enough to fit multiple Earths inside with room to spare. For the most massive black holes, this bubble grows so huge that it dwarfs entire solar systems. It is a reminder of how extreme the universe can be. When matter falls toward a black hole, it often forms a disk around the event horizon. This disk is called an accretion disk, and it glows brightly as the material heats up from friction and pressure. Even though the black hole itself is completely dark, the glowing disk makes it possible to see where the black hole is located. In some cases, the disk is so hot that it shines brighter than the entire galaxy around it. This effect helps astronomers measure the size of the black hole, and, by extension, the size of its event horizon. The brighter and larger the disk, the more massive the black hole must be. The Event Horizon Telescope, a network of radio telescopes across the globe, captured the first image of a black hole's shadow in 2019. The image showed the supermassive black hole in the galaxy M87, which has a mass of about 6.5 billion suns. Its event horizon stretches about 23 billion miles across, roughly the same distance as the orbit of Uranus. This was the first time humans had ever seen direct evidence of an event horizon scale. The dark center of the image represented the shadow cast by the black hole, surrounded by a glowing ring of light from the accretion disk. If a spacecraft approached an event horizon, the effects of gravity would become overwhelming. Time would appear to slow down for the craft as seen by observers far away. To those inside the craft, time would seem normal, but they would never be able to escape once they crossed the boundary. The closer they got to the black hole, the stronger the tidal forces would become. These forces stretch objects in a process called spaghettification. For smaller black holes, this stretching happens well before reaching the event horizon. For giant black holes, the event horizon is so large that a spacecraft could cross it intact before being torn apart. Only much later, as it moves closer to the center, would the tidal forces destroy it completely. The event horizon marks the limit of what we can observe. Light from objects outside the boundary can still escape, so we can see the glowing material swirling near the edge. But light from inside the event horizon cannot reach us, making it impossible to know what happens beyond that point. This makes black holes some of the most mysterious objects in the universe. The sheer size of the event horizon in the biggest black holes adds to this mystery. A boundary that can stretch beyond the size of a solar system shows how gravity can shape space on scales almost too vast to imagine. These enormous regions remind us that the universe operates on levels far beyond our everyday experience, where distances and forces reach extremes that defy ordinary understanding. The larger a black hole grows, the quieter it can seem. At first, this may sound strange. With so much mass and such a powerful pull of gravity, it would be easy to imagine a giant black hole as violent and dramatic. Yet the truth is often the opposite. The biggest black holes can appear calm and dark, almost invisible, making them much harder to detect. Their size allows them to consume matter without creating the bright displays we often see from smaller black holes. The result is a silent presence at the heart of a galaxy, hidden in plain sight. Black holes become visible to us not because of the black hole itself, but because of the material falling into it. When gas, dust, or even entire stars get too close, they form an accretion disk around the black hole. This disk heats up as particles collide and compress, releasing energy as light and radiation. In some cases, this light can shine brighter than every star in the galaxy combined. Quasars are the most extreme examples of this process, with supermassive black holes feeding so rapidly that they create enormous glowing beacons visible across the universe. But as a black hole grows even larger, it does not always continue to shine more brightly. Instead, it may consume matter so slowly and steadily that little light escapes. Imagine a campfire. When you toss a handful of dry twigs onto the flames, they flare up quickly, producing bright sparks and intense heat. This is like a smaller black hole feeding rapidly on fresh material. Now picture adding a single large, solid log to the fire. The fire burns more evenly and with less visible activity, even though the log contains far more fuel. A massive black hole behaves like that log. Its immense gravity allows it to pull matter inward in a smooth, steady way. The process produces less visible light, so from a distance, it appears much dimmer than a smaller, more active black hole. The center of our own galaxy provides an example. Sagittarius A, the supermassive black hole at the heart of the Milky Way, has a mass of about 4 million suns. Despite this, it is relatively quiet. Astronomers using powerful telescopes have observed only faint flares of light from material falling toward it. Most of the time, Sagittarius A remains dark and still. This quiet state makes it challenging to study. It was not discovered by its glow, but by watching how stars near the center of the galaxy move. These stars orbit an unseen point at incredible speeds. Their motion reveals the hidden presence of the black hole, even though it produces very little light on its own. As black holes grow larger, their event horizons also expand. The event horizon is the point of no return, the boundary where gravity becomes so strong that nothing can escape. A bigger event horizon gives matter more space to fall without colliding or heating up. In smaller black holes, incoming gas and dust compress tightly, creating friction that produces visible radiation. In the largest black holes, matter can slip past the boundary more gently, with less energy released on the way in. This makes the black hole even more difficult to detect because there is less surrounding light for telescopes to capture. Some of the most massive black holes known may have event horizons larger than our entire solar system. For these giants, even a large amount of falling material may not create much visible activity. The sheer scale spreads out the energy, preventing the kind of bright bursts seen around smaller black holes. From our point of view, the area may appear almost completely dark, with no obvious signs that anything is there at all. Astronomers rely on indirect methods to find these quiet giants. One technique involves tracking the motion of stars near the center of a galaxy. If the stars move in unusual ways, such as speeding up or orbiting in tight loops, it suggests the presence of a massive but invisible object. This method helped confirm the existence of Sagittarius A. Over many years, scientists mapped the paths of individual stars near the galactic center and found they were circling an unseen mass with incredible speed. The only explanation was a black hole. Another way to detect quiet black holes is through their gravitational effect on entire galaxies. A black hole with billions of solar masses can influence how gas flows through a galaxy and where stars form. In some cases, the black hole may release powerful jets of particles, even if its accretion disk is faint. These jets can stretch for thousands of light years and are easier to detect than the black hole itself. By tracing them back to their source, astronomers can identify the black hole's location, even if the central region appears dark. Consider two galaxies colliding. During the merger, gas and stars are pulled toward the centers of the combined system. If the black hole there is smaller, the rush of incoming matter creates bright flares of light, making it easier to spot. If the central black hole is already enormous, it swallows the incoming material more quietly. The event horizon is so large that the matter disappears without producing dramatic bursts of radiation. From a distance, this galaxy merger might look surprisingly calm, even though vast amounts of material are falling into the black hole. The quiet nature of massive black holes creates challenges for research. Detecting a faint source of light from billions of light years away is difficult, even with modern telescopes. This is why some of the largest black holes remain hidden. Their very size makes them less obvious. They do not announce their presence with bright flashes or loud signals. Instead, they sit in darkness, slowly shaping the galaxy around them through their immense gravitational influence. Imagine walking into a dark room. A small flickering candle catches your attention right away, while a large, silent figure standing in the shadows goes unnoticed. The candle is like an active, smaller black hole, while the silent figure represents a giant, quiet black hole. Even though the figure is much larger, you only notice the smaller, brighter source of light. This is how astronomers sometimes overlook the biggest black holes. They are there hidden in the dark, but they produce little direct evidence of their presence. The difficulty of finding these quiet giants has led scientists to develop new ways of studying them. In 2019, the Event Horizon Telescope captured the first image of a black hole's shadow. It targeted the black hole in the galaxy M87, which has a mass of about 6.5 billion suns. Even though this black hole is huge, it produces only limited visible light. The image showed a dark center surrounded by a glowing ring created by the bending of light around the event horizon. This was a major step forward in detecting and studying black holes that appear inactive. Gravitational waves offer another path. When two black holes merge, they create ripples in space itself. These waves travel outward and can be detected by sensitive instruments on Earth. Even if the black holes are dark and quiet, their collision sends a powerful signal. This method allows scientists to detect black holes without relying on light at all, which is especially useful for studying the largest and least active ones. The bigger a black hole grows, the more it blends into its surroundings. Its vast event horizon swallows light, while its feeding process becomes smoother and less visible. From a distance, it may look like an empty void, a silent region with little activity. Yet beneath that calm appearance lies an object of incredible power. shaping the galaxy around it in ways that are subtle but far-reaching. These giants remind us that in the universe, what is most powerful is not always what shines the brightest. Many of the largest black holes in the universe are silent, hidden giants. These colossal black holes sit at the centers of galaxies, but do not always feed on nearby matter. When a black hole is not actively consuming gas, dust, or stars, it gives off very little radiation. Without this activity, it becomes almost invisible to our telescopes. These quiet black holes are called dormant because, like a sleeping volcano, they wait silently, holding immense power while showing few outward signs of their presence. A black hole becomes visible only when matter falls toward it. As gas and dust spiral inward, they form an accretion disk. The material in this disk heats up as particles collide and compress. This heat produces intense light and radiation, which telescopes can detect across vast distances. In some cases, the energy released is so great that the center of the galaxy glows brighter than all its stars combined. These active black holes are dramatic and easy to spot. Like a fire burning brightly in the dark, dormant black holes, by contrast, are like unlit coals. The fuel may be there, but without heat or motion, they remain dark. Consider the difference between a bustling city and a quiet desert. A city at night is full of lights, noise, and motion. You can see it from far away because it shines brightly. A desert, even if it is vast, remains silent and dark. Active black holes are like the city. While dormant ones are like the desert, they both exist, but only one announces itself with obvious signs. The other must be found through subtle clues. The supermassive black hole at the center of our own Milky Way galaxy, Sagittarius A, is mostly dormant. It has a mass about 4 million times greater than the Sunday, yet it emits only faint bursts of radiation. Most of the time, it sits quietly, consuming very little material. If a large cloud of gas or a star were to drift too close, Sagittarius A would flare up temporarily as it pulled the matter inward. For now, it remains like a giant in deep sleep, its presence revealed only by the way nearby stars move under its gravity. By tracking these stars over many years, astronomers have been able to map their orbits and calculate the mass of the hidden object they circle. This is how they confirmed the existence of Sagittarius A, even though it produces almost no light. The size of a black hole plays a role in how it behaves. Smaller black holes, such as those formed from collapsing stars, have a stronger effect on nearby material relative to their size. They tend to create hotter, more active accretion disks, which glow brightly in X-rays and other high-energy forms of light. This makes them easier to detect, even if they are thousands of light years away. A massive black hole, on the other hand, can swallow matter in a calmer, more gradual way. Its event horizon is so large that material may cross it without creating intense bursts of heat or light. As a result, the black hole stays dark even as it feeds, and from a distance it appears dormant. Sometimes, a dormant black hole can suddenly become active if it encounters a fresh supply of material. Imagine a bear in hibernation. During the winter, it stays still and quiet, using little energy. When spring arrives and food becomes plentiful, the bear wakes up and begins to eat. A black hole behaves in a similar way. When little matter is nearby, it remains quiet. But if a star drifts too close, or two galaxies collide, a surge of gas may fall toward the black hole. This inflow of material can awaken the black hole, turning it into a bright, active center, known as an active galactic nucleus. After the supply of fuel runs out, the black hole returns to dormancy. In some galaxies, evidence of past activity can be seen, even if the black hole is currently quiet. For example, Astronomers sometimes find giant bubbles of gas extending far from the galactic center. These structures suggest that at some point in the past, the black hole released powerful jets of energy. The jets may have stopped long ago, but the marks they left behind remain, like footprints in the sand. By studying these remnants, scientists can piece together the history of the black hole's activity. The challenge with dormant black holes is that they hide so well. Without bright flares of radiation, they must be found through indirect signs. One method is to observe the motion of stars near the galaxy's center. If stars move in fast, tight orbits around an unseen point, it suggests a massive object is there. This is how Sagittarius A was discovered. Another method involves looking for gravitational effects on large scales. A black hole with billions of solar masses can influence how gas flows through a galaxy. By studying the patterns of this motion, scientists can infer the black hole's presence, even if they cannot see it directly. Some of the most massive black holes ever discovered are dormant. These giants may weigh tens of billions of times more than the Sun. If one of these black holes were at the center of our solar system, its event horizon, the boundary beyond which nothing can escape, would stretch far beyond Pluto's orbit. Despite their enormous size, they may give off very little light if they are not actively feeding. This makes them incredibly difficult to detect. Only by studying the stars and galaxies around them can astronomers find the subtle signs that reveal their locations. Dormant black holes play an important role in the life cycle of galaxies. When they are active, they can release huge amounts of energy, driving winds and jets that shape the galaxy's structure. These outbursts can push gas away, stopping the formation of new stars for millions of years. When the black hole becomes dormant, star formation may begin again as gas settles back into the galaxy. This back and forth cycle helps explain why galaxies evolve the way they do. Even in their quiet phases, dormant black holes remain central to the behavior of their host galaxies. Imagine a massive whirlpool in the middle of a calm lake. When water flows quickly into the whirlpool, it churns and spins, creating waves and splashes that are easy to see. When the inflow slows, the whirlpool becomes smooth and nearly invisible. The water is still moving, but it no longer creates obvious signs of motion. A dormant black hole is like that quiet whirlpool. Its gravity continues to pull on nearby objects, but without a supply of falling matter, it blends into its surroundings. Detecting these hidden giants requires patience and precision. Telescopes must measure tiny changes in the positions of stars or faint emissions of light from the galactic center. Over time, these small clues build a picture of the invisible object. In 2022, the Event Horizon Telescope produced the first image of Sagittarius A. Even then, the picture showed only a faint ring of light around a dark core. The darkness itself represented the black hole, a silent region from which no light escapes. Dormant black holes remind us that the universe is full of unseen forces. They may sit quietly for millions of years, shaping galaxies through their gravity while giving off almost no light. When they do awaken, the change can be sudden and dramatic, but most of the time they remain hidden, waiting in silence. Their true scale known only through careful observation and indirect evidence. Their presence is a reminder that what we cannot see can still have a profound impact on the cosmos. The largest black holes may be hidden at the centers of the biggest galaxies, deep inside galaxy clusters. A galaxy cluster is a vast collection of galaxies bound together by gravity. These clusters can contain hundreds or even thousands of galaxies, along with enormous amounts of gas and dark matter. At the heart of many of these massive galaxies sits a black hole of staggering size, possibly reaching tens of billions of times the mass of our Sun. These black holes are so powerful and so distant that they are often cloaked in darkness, invisible to direct observation. A galaxy cluster is like a city made up of many neighborhoods. Each neighborhood represents a galaxy filled with stars, planets, and clouds of gas. In the very center of this cosmic city, there is often a dominant galaxy called the brightest cluster galaxy. This galaxy is usually the largest and oldest member of the cluster, and it has grown by merging with many smaller galaxies over billions of years. Each time a merger happens, the central black holes of the colliding galaxies sink toward the center and combine. Over time, this process can create one enormous black hole at the heart of the brightest galaxy. The result is a hidden giant whose mass may be so extreme that its event horizon stretches far beyond the size of our solar system. Despite their immense size, these central black holes are often difficult to detect. Their very location makes them hard to study. The centers of galaxy clusters are crowded regions filled with gas, dust, and stars. This material blocks light, making it harder for telescopes to get a clear view. In addition, the black holes may not be actively feeding on matter. Without a strong supply of gas falling inward, there is little heat or radiation to reveal the black hole's presence. Even a black hole weighing billions of solar masses can remain quiet and dark if it has no nearby fuel. In these cases, scientists must rely on indirect evidence to find it. One method astronomers use is to study the movement of stars near the galaxy's center. Stars respond to gravity. So if they are orbiting an unseen object at very high speeds, it suggests something massive is there. By measuring the speed and pattern of these orbits, scientists can estimate the mass of the hidden black hole. This is how the black hole in our Milky Way, Sagittarius A, was confirmed. At a much larger scale, the same technique can reveal the presence of a black hole in a cluster's central galaxy. However, because these galaxies are much farther away, the measurements are more difficult and require extremely sensitive instruments. Another clue comes from the gas that fills the space between galaxies in a cluster. This gas is extremely hot, reaching millions of degrees, and it emits X-rays that can be detected by space telescopes. When a supermassive black hole at the center of the cluster becomes active, it can release powerful jets of particles. These jets carve out vast cavities in the surrounding gas, like holes in a cloud of smoke. Even when the black hole itself remains dark, the shape of these cavities can reveal its past activity. By studying these structures, scientists can learn how often the black hole was active and how much energy it released over time. Consider the galaxy cluster known as Abell 85. At its center lies one of the largest black holes ever measured, with a mass of around 40 billion suns. This black hole is hidden inside the brightest galaxy of the cluster. Most of the time, it remains dormant, consuming little material and giving off minimal light. Its presence is known only because of the way the surrounding stars move and the enormous influence it has on the cluster's central region. Without these clues, it would be completely invisible. These hidden giants play a key role in shaping their environment. When they are active, they can release bursts of energy so powerful that they affect the entire galaxy cluster. The jets from an active black hole can push gas outward, heating it and preventing it from cooling. Without cool gas, new stars cannot form, which changes how the galaxy evolves. Even when the black hole is dormant, its gravity still controls the motion of stars and gas over vast distances. It acts like the anchor of the cluster, holding the surrounding material in place. Imagine a giant whirlpool in the middle of a calm sea. From a distance, the water may look smooth and still. Only by watching the movement of nearby boats and waves can you tell that something powerful lies beneath the surface. A hidden black hole works in the same way. The region around it may appear quiet, but the motion of stars and gas reveals the strength of the invisible force at the center. The discovery of black holes in galaxy clusters has helped explain why some of these massive systems behave the way they do. For example, astronomers have observed clusters where star formation seems to have stopped entirely. In these cases, The central black hole may have released so much energy in the past that it heated the surrounding gas, making it impossible for the gas to cool and form new stars. Even after the black hole becomes dormant, the effects of its earlier activity can last for billions of years. This shows that black holes are not just local features of their galaxies, but also influence structures on much larger scales. Detecting these giants is a slow and challenging process. Astronomers use different types of telescopes to gather as much information as possible. Optical telescopes track the movement of stars, while X-ray telescopes study the hot gas in the cluster. Radio telescopes can map the faint signals from jets and cavities created by past black hole activity. By combining all these observations, scientists build a detailed picture of the hidden object at the center. Each piece of data adds to our understanding, much like assembling a puzzle one small piece at a time. The black hole at the center of the galaxy M87 is a well-known example. This black hole has a mass of about 6.5 billion suns and sits in the core of the Virgo cluster. In 2019, the Event Horizon Telescope captured the first image of its shadow, revealing the outline of the event horizon surrounded by glowing material. This was a historic moment in astronomy, providing direct visual evidence of a supermassive black hole. Even so, M87's black hole is only one of many such giants hiding in galaxy clusters across the universe. Some may be far larger, but they remain out of reach for now, cloaked by distance and darkness. When two galaxy clusters merge, their central black holes may eventually come together as well. This process takes billions of years, and as the black holes spiral inward, they release gravitational waves, ripples in the fabric of space. These waves can be detected by sensitive instruments on Earth. Even if the black holes themselves cannot be seen, their collision leaves a signature that travels across the universe. This gives astronomers another way to study these hidden giants and learn about their growth. The centers of galaxy clusters are some of the most extreme environments in the cosmos. They are crowded with stars, gas, and dark matter. Yet the black holes that live there are often completely dark. Their presence is felt through their gravitational pull, their past eruptions of energy, and the quiet way they shape the galaxies around them. Finding and studying them is like searching for a single heartbeat in a storm. These hidden giants remind us that the most powerful forces in the universe are not always the ones we can see. Among the most extreme objects in the universe, black holes stand out as true cosmic monsters. Some are so massive that even trying to imagine their size challenges our sense of scale. One of the most staggering examples known today is TUN 618, an ultramassive black hole located billions of light years from Earth. TUN 618 has a mass of roughly 66 billion suns. That number is almost impossible to picture. If our Sunday were the size of a single grain of sand, TUN 618 would be a mountain made entirely of sand stretching far beyond the horizon. It is one of the heaviest black holes we have measured, and yet it might not be the largest that exists. TUN 618 lies at the heart of a quasar, which is a galaxy with an active supermassive black hole at its center. A quasar shines so brightly because matter falls toward the black hole at incredible speeds. As the gas and dust spiral inward, they form an accretion disk that heats up due to friction. This disk releases enormous amounts of energy, often outshining the combined light of every star in its galaxy. The fact that TUN 618 is powering a quasar this bright tells us just how massive and active it is. It is so far away that the light we see from it today began its journey over 10 billion years ago. When we observe TUN 618, we are looking back in time to an era when the universe was young and galaxies were still forming. To understand what a mass of 66 billion suns means, consider the black hole at the center of our own Milky Way, Sagittarius A. It has a mass of about 4 million suns. This is huge compared to stellar black holes, which usually have only a few solar masses, yet Sagittarius A is tiny compared to Ton 618. You would need more than 16,000 black holes, the size of Sagittarius A, to equal the mass of Ton 618. The difference between the two is like comparing a small hill to the tallest mountain on Earth. The Milky Way's black hole might control the motion of nearby stars, but a black hole like Ton 618 dominates on an entirely different level. The size of its event horizon, the boundary beyond which nothing can escape, is equally staggering. For Ton 618, the event horizon would stretch hundreds of billions of miles across. If you placed it at the center of our solar system, the point of no return would extend far past Pluto's orbit and deep into the outer regions, where icy bodies drift in the Kuiper belt. Everything inside that vast sphere would be trapped forever. This scale is so large that entire planetary systems, along with countless stars, could vanish inside without a trace. Astronomers discovered Ton 618 by studying its quasar's light. They noticed that the light had been stretched and shifted due to the expansion of the universe. By measuring this redshift, they could calculate its distance and the incredible power it was emitting. The brightness and energy of the quasar told them that the central black hole had to be unbelievably massive. This was one of the first times a black hole of this size had been identified. Even now, Ton 618 remains a benchmark for what we consider ultramassive, but Ton 6, the 18th of May, not be alone at the top. There could be even larger black holes hidden in the universe. Some may be dormant, not actively feeding on matter, and therefore much harder to detect. Without a bright accretion disk, they blend into the darkness, revealed only through the way they affect surrounding stars and gas. These hidden giants could exceed even the mass of Ton 618, reaching levels that challenge current theories of how black holes grow. Black holes grow through two main processes, accretion and mergers. Accretion happens when gas and dust fall steadily toward the black hole, adding to its mass over time. Mergers occur when two black holes collide and combine into one in the crowded centers of galaxy clusters, where galaxies frequently interact. Both processes can take place repeatedly over billions of years. Each collision adds more mass, like raindrops merging into a river. A black hole like Ton 618 likely formed through this gradual, relentless growth. If a galaxy cluster had enough material and enough time, an even larger black hole could form, possibly with a mass approaching 100 billion suns or more. Imagine a city filled with skyscrapers. Each building represents a black hole. When two buildings merge, they form a taller structure. Over time, as more buildings combine, a single towering skyscraper rises above the rest. A galaxy cluster works the same way. Smaller black holes merge and grow, eventually creating one colossal structure at the center. Ton 618 is like one of these towers, but somewhere in the universe, there may be an even taller one that we have yet to see. Detecting such a black hole is difficult. Astronomers look for indirect evidence, like the motion of stars near the galactic center, or the shape of gas clouds affected by gravity. They also search for the signatures of past activity, such as giant cavities carved into surrounding gas by jets of particles. In some cases, they detect gravitational waves, ripples in space caused by the collision of massive black holes. These signals can travel across the universe, reaching Earth billions of years after the event. Even if a black hole is completely dark, its collision with another leaves behind a clear mark in the fabric of space. One example of a hidden giant is the black hole in the galaxy home 15A. This black hole has an estimated mass of around 40 billion suns, making it one of the heaviest measured so far. It does not shine as brightly as a quasar, which makes it harder to detect. Its presence was confirmed by studying the motion of stars near the center of the galaxy. This shows how even colossal black holes can remain hidden when they are not actively feeding. Comparing these black holes helps astronomers understand how galaxies evolve. The relationship between a galaxy and its central black hole is complex. When the black hole is active, it can release energy that shapes the galaxy's structure. Jets of particles can heat surrounding gas, preventing it from cooling and forming new stars. This process can halt star formation for millions of years. When the black hole becomes dormant, star formation can resume. By comparing active systems like TUN 618 to quieter ones like HOME 15A, scientists gain insight into these cycles of growth and rest. The sheer scale of TUN 618 forces us to rethink our place in the universe. The entire Milky Way contains about 100 to 400 billion stars. TUN 618 alone outweighs a sixth of those stars combined. If our entire galaxy were somehow funneled into its event horizon, a significant portion of its mass could vanish into darkness. It is not just a black hole. It is a gravitational engine that holds sway over its entire region of space. There is also the possibility that somewhere beyond our reach, even more massive black holes exist. These could be lurking in the centers of the largest galaxies within the most crowded galaxy clusters. Because they may not be feeding actively, they could remain completely hidden, their vast event horizons invisible against the backdrop of space. Only the motion of nearby stars or the detection of gravitational waves might reveal their presence. Until we find them, TUN 618 remains our best known example of how large a black hole can grow. It stands as proof that the universe contains forces so immense they can barely be measured, let alone fully understood. Some black holes may be so distant or so silent that they remain forever beyond our reach. Even with the most advanced telescopes and detectors, we might never confirm their existence. The universe is vast, and light takes time to travel across it. When we look at distant galaxies, we are seeing them as they were billions of years ago. There are places so far away that the light from them has not had enough time to reach us since the beginning of the universe. Any black holes in those regions are hidden simply because their signals have not yet arrived. They exist beyond the limits of what we can observe. Distance is not the only barrier. Some black holes are quiet by nature. A black hole becomes visible to us when matter falls toward it. Gas, dust, or even stars spiral inward, forming an accretion disk that heats up and shines. This glow can reveal the black hole's location. Quasars are extreme examples of this process. Their central black holes feed so rapidly that they produce dazzling light visible across billions of light years. But not all black holes are this active. Many consume matter slowly or not at all. Without an accretion disk or jets of particles, a black hole emits almost no radiation. It fades into darkness, leaving only its gravity to mark its presence. Even nearby, a quiet black hole could be hard to detect. At great distances, it becomes nearly impossible. Imagine walking through a dark forest at night. You can see the glow of campfires in the distance, but the animals moving silently in the shadows remain unseen. The bright campfires are like active black holes, their light reaching you clearly. The hidden animals are like dormant black holes, present but invisible. You know they are there only if you hear a branch snap or catch a fleeting movement. In space, those hints come from indirect effects. Astronomers track the motion of stars and gas to infer the presence of a massive unseen object. This method works well for galaxies within our local region of the universe, but at extreme distances, the signals grow faint, and the movement of individual stars becomes impossible to measure. Gravitational waves offer another way to detect black holes. When two black holes collide, they send ripples through space itself. Instruments on Earth, such as LIGO and Virgo, can detect these waves. The first confirmed detection came in 2015 from the merger of two black holes about 1 billion light years away. This proved that even completely dark black holes could be studied through their collisions. Yet this method also has limits. If a black hole never collides or its collision happens too far away, the waves may be too weak to reach us. The event passes silently, unnoticed, like a whisper lost in a storm. Some black holes may exist in regions so obscured by dust and gas that no light escapes to reveal them. The centers of galaxy clusters are often crowded and chaotic. Thick clouds of matter block our view, hiding what lies inside. Even powerful space telescopes struggle to see through these barriers. In some cases, astronomers rely on X-rays or radio waves, which can penetrate the clouds better than visible light. But if the black hole is quiet and produces little radiation, even these methods fail. It remains hidden, like a stone buried deep beneath layers of soil. The size of the black hole can make detection harder, not easier. A smaller black hole with a strong flow of incoming matter can create a bright active disk. The heat and radiation make it stand out against the darkness of space. A larger black hole, especially one with an enormous event horizon, can consume matter more gently. The material falls inward smoothly. From a distance, there may be no visible sign at all. A giant black hole could sit at the center of a galaxy, swallowing stars and gas in silence, leaving no clear trace for us to see. There is also the problem of time. Light and other signals do not just travel across space, they also stretch as the universe expands. This stretching, called redshift, makes distant signals fainter and harder to detect. At extreme distances, the light may shift so much that it moves into ranges. Our instruments cannot measure. The black hole's activity might have been intense billions of years ago, but by the time its signal reaches us, it has faded to almost nothing. In this way, even active black holes can become invisible simply because of how far their light must travel. Consider how difficult it is to study something, even within our own galaxy. The supermassive black hole at the center of the Milky Way, Sagittarius A, yet it took decades of careful observation to track the movement of stars around it and confirm its presence. Capturing the first image of its shadow required linking radio telescopes across the entire planet. If finding and studying Sagittarius A is this hard, then detecting a quiet black hole billions of light years away becomes almost impossible. Some black holes might also form in ways that make them harder to detect. The earliest black holes may have appeared soon after the universe began, created from the direct collapse of massive clouds of gas. These black holes could have started out large, giving them a head start in growth. If they sit in regions with little surrounding material, they might stay quiet for billions of years. Without active feeding, there is nothing to light them up. They would drift through space like invisible anchors, shaping galaxies through gravity alone. Galaxy clusters may contain some of the most massive black holes hidden at their centers. These clusters are like cosmic cities, each with a central district packed with stars, gas, and dark matter. The dominant galaxy in the middle often holds a giant black hole, built up through countless mergers. In some clusters, these black holes weigh tens of billions of solar masses. When active, they can power quasars visible across the universe. When dormant, they fade completely into the background. Astronomers must rely on the movement of entire galaxies or the shape of the surrounding gas to guess at their size. Even then, the estimates are uncertain. A black hole larger than any we have measured could be hiding there, unseen. Technology continues to improve, giving us new ways to search. Telescopes like the James Webb Space Telescope can see farther and in more detail than previous instruments. Future gravitational wave detectors will be even more sensitive, able to catch signals from events happening at greater distances. Yet no matter how advanced our tools become, there will always be limits. The universe is expanding, and some regions are moving away from us faster than the speed of light. Any light or wave from beyond that boundary can never reach us. Black holes in those regions are permanently hidden, beyond measurement in every sense. Imagine standing on a shore at night, looking out across a vast ocean. You see the glow of distant ships and lighthouses, but beyond a certain point, everything fades into darkness. You know, there are more ships out there, but their lights are too far away to reach your eyes. The ocean continues endlessly, filled with unseen activity. The universe works the same way. The black holes we can see are like the ships near the shore. Beyond them lies a realm of complete darkness, where objects exist but remain forever out of sight. Some black holes will always stay in that realm, too far or too quiet to ever reveal themselves. Black holes are some of the most mysterious objects in the universe, and one reason for this is their ability to hide. A black hole itself does not produce light. It has no surface, no glowing layer, and no way to emit radiation on its own. Light cannot escape its gravity once it passes the event horizon, the boundary where escape becomes impossible. This means that a black hole is naturally dark. The only time we can see evidence of a black hole is when it interacts with surrounding matter. If gas, dust, or stars fall toward it, they release energy as they heat up. And that glow gives us a way to detect the black hole's presence. Without that material nearby, a black hole becomes effectively invisible. It turns into a cosmic shadow hidden against the backdrop of space. Most black holes are found because of their effect on nearby matter. When gas spirals inward, it forms an accretion disk. The particles in this disk rub against each other, creating friction and intense heat. This heat produces light and other forms of radiation, like X-rays. Telescopes detect this radiation and trace it back to its source. This is how astronomers discovered many stellar black holes in our galaxy, and how they identified supermassive black holes in distant galaxies. In some cases, the activity is so extreme that the area around the black hole shines brighter than every star in the galaxy combined. These bright active regions are called quasars. They are like cosmic lighthouses, easily seen across billions of light years. But when there is nothing nearby for a black hole to consume, there is no disk, no heat, and no light. In these cases, the black hole is completely dark. It gives off no detectable signal. Space is filled with countless black holes that may be in this state right now. They drift silently through the galaxy, influencing their surroundings only through gravity. From Earth, they are invisible, unless they pass in front of something brighter or interact with other objects. This makes finding them a tremendous challenge. Imagine walking into a dark cave. If there are torches burning, you can see the walls, the floor, and the shapes around you. If all the torches go out, everything disappears into pitch blackness. You can still feel the cave's walls, but you cannot see them. A black hole without surrounding matter is like a cave without torches. Its presence is still there, but there is no light to reveal it. Only by feeling its effects indirectly can you tell where it is. One way scientists detect these dark black holes is by watching the motion of stars. Stars near a black hole move in specific ways, speeding up as they approach the strong gravitational field. By tracking these motions over time, astronomers can calculate the mass of the object they orbit. If that mass is too great to be explained by normal stars or clusters of stars, it suggests a black hole. This is how the supermassive black hole at the center of our Milky Way, Sagittarius A, was confirmed. Over many years, astronomers mapped the paths of stars near the galactic center. They found that the stars were circling an unseen point with incredible speed, revealing the presence of a massive object about 4 million times the mass of the Sun. For black holes that are not at the centers of galaxies, the task is harder. Stellar black holes can wander through space alone. If they are not actively pulling material from a nearby star, they remain hidden. Occasionally, a star may pass behind a black hole from our perspective. The black hole's gravity bends the star's light, a phenomenon called gravitational lensing. This creates a temporary brightening that astronomers can detect. By carefully studying these lensing events, they can identify otherwise invisible black holes. However, such events are rare and require precise timing. The difficulty of detecting these cosmic shadows means there are likely many more black holes than we have found. Estimates suggest there could be hundreds of millions of stellar black holes in our galaxy alone. Most of them are dark and dormant, with no visible activity. They drift like silent predators, only revealing themselves when something crosses their path. Even supermassive black holes can be invisible if they are not actively feeding. A galaxy may have a giant black hole at its center, but if there is little gas nearby, it will remain quiet. In these cases, astronomers must rely on indirect signs, like the way stars move near the core or the patterns of gas in the galaxy. The size of the black hole can make it even harder to find. Paradoxically, the largest black holes can be the quietest. Their event horizons are so large that material can fall inward smoothly without creating the intense heat and radiation that smaller black holes produce. This means a supermassive black hole could consume entire stars without giving off a dramatic flare of light. From a distance, the galaxy might appear calm, even though unimaginable forces are at work in its core. Consider a pond on a still day. If you throw in a handful of pebbles, ripples spread across the surface, and you can clearly see where the disturbance came from. Now imagine dropping a single large rock straight down into the center of the pond. The rock sinks smoothly, with little splash or noise from above. You might not notice anything at all. A massive black hole works like that large rock. Its feeding can be so smooth and quiet that there is no outward sign of what is happening. The universe is filled with regions that are dark for reasons beyond the black holes themselves. Thick clouds of dust and gas can block light, hiding what lies behind them. Even if a black hole is surrounded by matter, its glow might be concealed by these barriers. Astronomers use radio waves and X-rays to see through some of the fog. But these methods have limits. A truly isolated black hole far from other sources of light could remain undetected no matter how powerful our instruments become. Gravitational waves provide another tool for finding hidden black holes. When two black holes merge, they create ripples in space-time. These ripples travel outward at the speed of light. Instruments on Earth can detect them, giving us a way to study black holes without needing light at all. The first detection of gravitational waves came from two smaller black holes colliding about 1 billion light-years away. Even though those black holes were invisible, their merger sent a signal strong enough to reach us. However, if a black hole never merges or if it is too far away, this method cannot reveal it. Some of the most massive black holes may sit at the centers of galaxy clusters, surrounded by vast amounts of dark matter and hot gas. These environments are crowded and chaotic, making it hard to distinguish one black hole's influence from all the other forces at play. If the central black hole is quiet, it may disappear completely into the background. Only by studying the motion of entire galaxies within the cluster can astronomers estimate its size and presence. Even then, the numbers are uncertain. The concept of a cosmic shadow captures the essence of these hidden black holes. They are not gone or inactive in a physical sense. Their gravity continues to shape their surroundings. Stars orbit them, galaxies move under their influence, and space itself bends around them. Yet to our eyes and to our instruments, they are blank spots in the map of the universe. Their invisibility is not a trick of light, but a fundamental part of their nature. A black hole without surrounding gas or stars is like a silhouette against the night sky, defined only by what it hides and by the quiet, relentless pull it exerts on everything nearby. Telescopes are our eyes on the universe. They let us see objects that are far beyond the reach of our own vision. But even the most advanced telescopes have limits. The Event Horizon Telescope, or HT, is one of the most powerful tools ever built. It combines radio telescopes around the world into a single network the size of Earth. This technique, called very long baseline interferometry, gives it incredible resolution. It is the reason we were able to see the first image of a black hole's shadow. The supermassive black hole, at the center of the galaxy M87, that image, released in 2019, showed a dark circle surrounded by a glowing ring of hot gas. It was a historic moment and a major achievement for science. But even with this success, the EHT has limits. Black holes are incredibly far away, and they are also small compared to the vast distances that separate us from them. To capture an image, the telescope must be able to resolve details as tiny as the event horizon itself. The farther away a black hole is, the harder it becomes to do this. The M87 black hole was an ideal target because it is both very massive and relatively close by cosmic standards, about 55 million light-years away. Its event horizon is so large, around 23 billion miles across, that it appears just big enough for the 8 to capture. Most black holes, even supermassive ones, are too far away for this level of detail. The situation is like trying to photograph a coin on the surface of the moon. With the right equipment, you might barely make out its shape. Move the coin farther away, and no matter how powerful your camera is, it becomes a single point of light. A black hole works the same way. If it is distant or not massive enough, its shadow blends into the background, and the telescope cannot separate it from the surrounding space. Even if we built a larger network of telescopes, there would always be a limit to how much detail we could capture. The size of Earth sets a physical boundary on how big the network can be. To get sharper resolution, we would need telescopes in space, spread far apart, which is far more complex and expensive. Another challenge comes from the material around black holes. To image a black hole, we rely on the light emitted by the gas and dust swirling around it in the accretion disk. This material glows because of the intense heat generated as it spirals inward. Without it, there is nothing to see. A quiet black hole with little surrounding matter produces almost no signal for the EHT to detect. Even if the telescope had perfect resolution, it would still be looking at darkness. The black hole would remain hidden, like a bird in a dark forest that makes no sound and leaves no tracks. Even when a black hole is active, the light from its surroundings can be distorted by clouds of dust and gas between us and the black hole. These obstacles scatter and block the signal, blurring the final image. Astronomers must use complex algorithms to piece together the data and remove interference. This is similar to trying to see a mountain through thick fog. You might be able to make out its outline, but the details will always be uncertain. The M87 image is remarkable, but it represents the very best conditions and a huge amount of processing. For many black holes, the environment is far more chaotic, making a clear image almost impossible. The black hole at the center of our Milky Way, Sagittarius A, shows these challenges clearly. It is much closer than M87, only 26,000 light-years away. But it is also much smaller, about 4 million solar masses. Its event horizon is tiny compared to M87's. On top of that, Sagittarius A is surrounded by turbulent clouds of gas. The material moves quickly, changing shape in minutes or hours. This makes it difficult to capture a stable image. The EHT released its image of Sagittarius A in 2022, but it required extraordinary effort and advanced modeling to produce. Even then, the image is blurrier than the one of M87, showing how hard it is to see smaller black holes, even nearby ones. For the largest black holes, there is a different problem. These giants might have event horizons hundreds of billions of miles across, far larger than the orbit of Pluto. While their size is immense, they may also sit in the centers of distant galaxy clusters, hundreds of millions or even billions of light-years away. At those distances, their event horizons appear smaller than a single pixel in the HD's view. It does not matter how huge the black hole actually is. If it is too far away, the telescope cannot resolve its shape. It becomes like trying to distinguish the outline of a mountain from the surface of another planet. You might detect its presence through indirect means, like the motion of stars or the pattern of surrounding gas. But you will never see its shadow directly. Some black holes are hidden not only by distance, but by their quiet nature. A truly dormant black hole has no accretion disk, no jets of particles, and no bright flares of radiation. It sits silently in space, bending light and pulling on nearby objects, but offering no glow of its own. The EHT depends on that glow to create an image. Without it, there is nothing for the telescope to capture. Even the largest black holes could remain completely invisible if they are not actively feeding on matter. This is why so many black holes are discovered indirectly. By looking at how stars move, or by detecting gravitational waves from collisions. The image of a shadow is the rare exception, not the rule. Future telescopes may push these limits further. Plans exist to place radio telescopes in orbit, creating a network that stretches beyond Earth. This would increase resolution dramatically, like expanding the size of a camera lens. With such a system, we might image black holes that are currently beyond reach. Still, there will always be a boundary set by the speed of light and the expansion of the universe. Some black holes are simply too far away for their signals to ever reach us. Others are buried so deep in clouds of matter that even the clearest telescope cannot see through them. These barriers are part of the nature of the universe itself. Consider looking at a distant lighthouse across a stormy sea. If the light is bright and the air is clear, you can see it from far away. If the light is dim or the fog is thick, the lighthouse disappears from view, even though it is still there. A black hole works the same way. The EHT was able to capture the light of M87's glowing disk because conditions were just right. For other black holes, the light may be too faint, the distance too great, or the cosmic fog too dense. In those cases, no image is possible. The Event Horizon Telescope has shown us that direct imaging of a black hole is possible, but it has also revealed how rare and difficult such achievements are. The universe is filled with black holes, many of them larger than M87's, but they are scattered across unimaginable distances. Even with a telescope the size of Earth, most will remain beyond our sight. We can measure their effects and trace their influence, but their shadows will stay hidden, reminders of the limits of our instruments and the vastness of space. Some black holes may hide in the most silent corners of the universe, in places where galaxies have faded and gone dark. These galaxies are sometimes called galactic graveyards. They are no longer filled with young, bright stars or glowing clouds of gas. Instead, they are made of ancient stars that burn dimly, their light weak and scattered. The gas that once formed new stars is gone, either consumed or blown away by violent events long ago. These galaxies have become quiet relics, and within their cores, colossal black holes may remain cloaked in near total darkness. In their active past, these galaxies might have been bustling places. Billions of stars could have been born, lived, and died there. As massive stars collapsed, they left behind black holes of many sizes. Over billions of years, as the galaxy aged, these smaller black holes might have merged with one another or fallen toward the center. At the core, they would have fed a much larger black hole, growing it steadily over time. When the galaxy still had plenty of gas and young stars, the central black hole may have been a powerful engine, pulling in matter and creating bursts of energy that lit up the galaxy like a beacon. Eventually, the fuel supply ran out. The black hole consumed the nearby gas, or pushed it away with violent jets of radiation and particles. Without gas, star formation slowed and finally stopped. The brightest, hottest stars died first, leaving behind cooler, older stars that shined faintly. What was once a thriving galaxy became a dark, quiet place. The central black hole, now without a steady flow of material, grew dormant. It no longer has a glowing accretion disk or strong jets to reveal its presence. Instead, it sits silently at the center, its gravity still immense, but its activity hidden. These dormant giants are some of the hardest objects to find. Without light or radiation, there is nothing for our telescopes to capture. They do not announce themselves like active black holes in quasars or star-forming galaxies. Instead, they blend into the shadows, almost indistinguishable from the surrounding darkness. The only clues they leave behind are the movements of nearby stars. Astronomers can sometimes detect them by studying how those stars orbit. If the stars move in tight, fast loops around an unseen point, it suggests there is something massive hidden at the center. But in a galaxy that is already faint and far away, even these motions can be difficult to measure. Imagine an old abandoned city in the desert. The streets are empty and the buildings are crumbling. During the city's height, it was full of people, lights, and noise. Now it is silent, and only the remains of its structures reveal that it was ever alive. A galactic graveyard is like that city. The stars are the ruins, ancient and fading. The black hole at the center is like the last remaining tower, tall and imposing but hidden in the darkness. You know, it is there only if you search carefully and understand the traces it leaves behind. Some of the oldest galaxies we can see today are relics of a very young universe. When the universe was new, galaxies were small and chaotic. They collided often, merging into larger structures. These collisions helped grow both the galaxies and their central black holes. Over time, some of these galaxies burned through their supply of gas. The most massive stars exploded as supernovae, spreading heavy elements like iron and oxygen. These explosions enriched the remaining gas, but also blew much of it away. The central black holes, now extremely massive, may have released jets and winds that pushed out the rest of the gas. With no fuel left, the galaxy went dark. Black holes in these ancient galaxies can reach extraordinary sizes. Some may have masses of tens of billions of suns. If one of these giants were placed at the center of our solar system, its event horizon would extend far beyond Pluto's orbit. Yet despite this scale, it would remain invisible without matter falling into it. The black hole itself does not glow. It can only be detected by what it does to nearby objects. In a galaxy filled mostly with faint, old stars, those effects are subtle and easy to miss. Astronomers have found hints of these hidden giants by looking at clusters of galaxies. In some cases, the central galaxy of a cluster has a black hole so massive that it shapes the motion of surrounding galaxies. Even when the central galaxy is faint, its gravitational pull reveals that something extraordinary is there. Home 15A, a galaxy in the cluster, Abell 85, holds one of the largest black holes ever measured. It has an estimated mass of around 40 billion suns. The galaxy itself is dim and diffuse, with few signs of new star formation. The black hole at its core is mostly dormant, but its sheer gravity leaves a mark on everything around it. Detecting even larger black holes may require indirect methods. One approach is to study gravitational lensing, where a massive object bends the light of objects behind it. A quiet black hole in a dark galaxy could reveal itself by how it distorts the light from more distant galaxies. This method does not require the black hole to shine, only to bend space. It is like seeing a glass bottle, by the way. It warps the view of the scenery behind it. The effect is subtle, but with precise measurements. Astronomers can use it to infer the presence of otherwise invisible objects. Gravitational waves provide another way to uncover these hidden giants. When two massive black holes collide, they create ripples in space-time. These ripples spread outward at the speed of light. Instruments like LIGO and Virgo can detect them if they are strong enough. If a black hole in a galactic graveyard merges with another, the resulting waves might reach us even if no light accompanies them. This offers a rare glimpse into events happening in the darkest parts of the universe. The age of a galaxy affects how hard it is to study. Young galaxies are bright and full of activity. They contain glowing gas clouds, new stars, and often an active central black hole. Old galaxies, by contrast, are quiet and faint. Their stars are spread thin, and there is little gas to provide contrast. This makes them difficult to see, especially at great distances. It is like trying to spot the faint outline of a burned out candle in a room full of bright lamps. The candle is there, but its light is too weak to stand out. As galaxies fade, their black holes do not disappear. They continue to shape their surroundings through gravity, pulling on stars and influencing the motion of entire systems. These effects happen slowly, over billions of years, and are invisible to the human eye. Only with careful observation and powerful instruments can astronomers detect the subtle signs of these ancient forces at work. Even then, much remains hidden. The universe is vast, and many galactic graveyards may lie so far away that their signals will never reach us. In the quiet depths of space, these places tell a story of cosmic history. They are reminders of a time when galaxies were young and full of light, and of how that light eventually faded. The black holes at their centers are the last remnants of that earlier era, silent guardians of a past we can only glimpse. Though they hide among the oldest stars, their presence shapes the universe in ways we are just beginning to understand. They are the unseen hearts of galaxies long gone dark, waiting in the shadows for the day when we learn to find them. Black holes are among the most extreme objects in the universe, and their true scale is almost impossible to imagine. The event horizon, the boundary beyond which nothing can escape, marks the edge of a black hole. It is not a surface in the way we think of a planet's surface. It is an invisible point in space where gravity becomes so strong that even light cannot break free. The size of this boundary depends on the mass of the black hole. For the largest black holes, called ultramassive black holes, the event horizon could stretch billions of kilometers across. That distance is so vast that it dwarfs our entire solar system. Yet the black hole would still be completely dark unless matter was falling into it and heating up to produce light. To understand how large this is, imagine placing a black hole at the center of our solar system. The Sunday would be replaced by a point of intense gravity. If the black hole's mass were great enough, its event horizon could extend past the orbit of Pluto and far beyond the icy objects of the Kuiper belt. Everything inside that range would be trapped. Planets, moons, asteroids, and even light itself could not escape once they crossed that boundary. From Earth's point of view, there would be no visible wall or glowing edge. The sky would simply contain a region of perfect darkness, a silent sphere where nothing returns. Despite their immense size, black holes are hard to detect. The event horizon itself does not glow. It produces no light or heat of its own. The only way to see a black hole directly is through the material falling toward it. Gas and dust that spiral inward form what is called an accretion disk. Friction between the particles in the disk generates heat, making the material shine. The glow from this process can be so bright that it outshines every star in the surrounding galaxy. Without that glow, the black hole remains invisible. Even if its event horizon is billions of kilometers wide, it becomes like a vast black ocean in the middle of space, detectable only by the way it distorts the motion of nearby stars and gas. The relationship between a black hole's size and its visibility is a strange one. A small black hole, with just a few times the Sunday's mass, can appear active and bright if it is pulling matter from a nearby star. The intense heat from that material creates radiation that telescopes can detect. A much larger black hole might sit quietly swallowing stars and gas so smoothly that very little light escapes. From a distance, this massive black hole could appear completely dark, even though its event horizon is unimaginably vast. The size alone does not guarantee visibility. It is the activity around the black hole that determines whether we can find it. Consider how we first saw the shadow of a black hole. In 2019, the Event Horizon Telescope captured an image of the black hole at the center of the galaxy M87. This black hole has a mass of about 6.5 billion suns. Its event horizon stretches roughly 23 billion miles across, large enough that the EHT could resolve it as a dark circle surrounded by a glowing ring of hot gas. Even so, the image was blurry and faint, a result of pushing the limits of technology. For black holes even farther away, or larger but quieter, the task becomes nearly impossible. Without the glow of falling material, there would be no visible ring, no way to outline the shape of the event horizon. It would remain hidden, a shadow against the dark background of space. The sheer size of these event horizons challenges our understanding of scale. 1 billion kilometers is more than 6 times the distance from the Earth to the Sunday. Light travels at nearly 300,000 kilometers per second. Yet it would take hours to cross a boundary that wide. In human terms, this is a distance so great that it stretches the limits of comprehension. Even so, the event horizon is only a boundary, not a physical structure. A spacecraft passing it would not bump into anything or feel a sudden change. It would simply reach a point where escape becomes impossible, though to an observer far away, it would appear frozen at the edge, moving slower and slower as it approached. The invisibility of a black hole is not just about its lack of light. It is also about how it bends space itself. Gravity warps the path of light, curving it around the black hole. Some of the light from nearby stars may be deflected or even trapped in orbits around the event horizon. This creates strange optical effects, such as rings or arcs of distorted light, called gravitational lensing. These effects can help astronomers detect black holes indirectly. Even if the black hole itself is dark, the bending of light around it can reveal its location. However, for very distant or quiet black holes, even these clues can be faint and difficult to measure. Imagine standing in a field on a moonless night. A bright city glows on the horizon, easy to see from miles away. Closer to you, there is a deep, still lake. If the lake reflects the city lights, you can tell where it is. But if the lake is perfectly calm and dark, you might walk right past it without noticing. A black hole without surrounding matter is like that dark lake. It reflects nothing and emits nothing. Unless something nearby interacts with it, it blends completely into the surrounding space. Only by watching carefully for the way stars move or light bends can you guess where it is. The most massive black holes are often found at the centers of galaxy clusters. These clusters are cosmic cities containing hundreds or thousands of galaxies. At their core, the dominant galaxy usually holds a black hole of extraordinary size. Over billions of years, this black hole has grown by merging with others and swallowing vast amounts of gas. Its event horizon may reach billions of kilometers across, making it one of the largest single structures in the universe. Yet if it is not actively feeding, it may produce almost no light. From our perspective, the core of the cluster could appear calm, hiding a black hole so massive it shapes the motion of entire galaxies. Even with the most advanced technology, we face limits in detecting these giants. The farther away a black hole is, the smaller it appears to our instruments. Distance makes even the largest event horizons shrink to a single, unresolved point of darkness. Without a glowing accretion disk, there is nothing to outline the shape or reveal the boundary. This is why many black holes are discovered through indirect methods. Astronomers study the orbits of stars or the distribution of hot gas, looking for patterns that only a black hole's gravity can explain. These methods tell us that something is there. Even if we cannot see it directly, gravitational waves provide another way to study black holes. When two black holes merge, they create ripples in space itself. These ripples travel outward, carrying information about the size and mass of the objects involved. Instruments on Earth can detect these waves, giving us a glimpse of black holes that are otherwise completely invisible. Even so, this technique only works when a merger occurs. A single, quiet black hole remains hidden unless it interacts with something else in a dramatic way. The largest black holes are like cosmic ghosts. Their event horizons stretch across distances measured in billions of kilometers, yet they emit no light of their own. Without a glowing disk of infalling matter, they cannot be seen. They shape their surroundings through gravity alone, pulling on stars and bending the paths of galaxies. We know they exist because of their effects, but their true forms remain out of sight. They are boundaries without walls, immense regions of space defined by absence, silent and unseen, until the universe itself provides a way to reveal them. Black holes can grow to incredible sizes, but there may be a point where even the universe cannot support something larger. Astrophysicists debate whether there is a natural upper limit to how massive a black hole can become. The number often discussed is around 100 billion times the mass of our Sunday. Beyond this, some theories suggest a black hole could become unstable and collapse in ways we do not yet fully understand. This limit is not certain, and researchers continue to study how these giants form, grow, and potentially reach a point where they can no longer exist as stable objects. Black holes gain mass through two main processes: accretion and mergers. Accretion happens when gas, dust, and other matter fall steadily toward the black hole. As this material spirals inward, it forms an accretion disk and eventually crosses the event horizon, adding to the black hole's total mass. Mergers occur when two black holes collide and combine into a single larger one. Over billions of years, especially in dense regions like galaxy clusters, these processes can repeat many times. A black hole that starts small can grow into a supermassive black hole with billions of solar masses. This is how astronomers believe the largest black holes we know of, such as Ton 618, with its mass of about 66 billion suns, came to exist. The question is whether this growth can continue forever. At some point, the black hole's event horizon becomes so large that the physics around it changes. Some models suggest that when a black hole grows past a certain size, it begins to disrupt the very structure of the galaxy or cluster around it. The supply of gas may no longer be able to reach the center efficiently, slowing further growth. In this way, the environment itself could impose a natural limit, like a predator, that becomes so large it can no longer find enough food to survive. Another factor is the behavior of the accretion disk. As matter falls in, it heats up and produces radiation. This radiation pushes outward, countering the black hole's gravity. In smaller systems, gravity easily overcomes this pressure, and material continues to fall inward. But at extreme scales, the outward pressure might balance or even overwhelm the inward pull, effectively shutting off the feeding process. This limit is similar to what happens in stars, where radiation pressure prevents a star from growing endlessly. In black holes, the process is more complex, but the principle is similar. Growth slows or stops when the balance of forces shifts. Some theories go further and suggest that black holes above a certain mass might become physically unstable. Space-time itself may not be able to support such a concentration of energy in one place. If this is true, a black hole that crosses the threshold might undergo a dramatic change. Instead of remaining a single, coherent object, it could fragment, release energy, or collapse into a new form we have not yet observed. These ideas are highly speculative because we have no direct evidence of black holes near this upper limit. Still, they are grounded in our current understanding of general relativity and quantum mechanics. Two pillars of modern physics. To picture the scale, consider what a black hole of 100 billion solar masses would mean. The event horizon of such an object would be vast, stretching billions of kilometers across. If it were placed at the center of our solar system, the point of no return would extend far beyond the orbit of Pluto, swallowing everything we know. Even light would take hours to travel across its boundary. This is a single object so massive that it would outweigh entire galaxies. The energy released as it consumed material would be staggering, potentially disrupting the structure of its host galaxy, and even affecting nearby galaxies in a cluster. The largest black holes we have confirmed so far are still below this theoretical limit. TON 618, for example, is around 2/3 of the way there at 66 billion solar masses. The black hole in the galaxy home 15A is estimated to be about 40 billion solar masses. These are already beyond what many scientists expected to find, suggesting that growth can continue to extreme levels under the right conditions. If these giants exist, it raises the question of whether even larger ones could form, given enough time and material. The early universe, with its dense clouds of gas and frequent galaxy mergers, may have been an ideal environment for rapid black hole growth. If so, there might be ultramassive black holes hiding in distant regions of space that have not yet been detected. Finding them is difficult. A truly massive black hole does not always produce a bright signal. If it has little surrounding material to feed on, it can remain dark and quiet. Even with modern telescopes, it would be nearly invisible, detectable only through its gravitational effects. Astronomers look for clues such as the motion of stars or the distribution of hot gas in galaxy clusters. In some cases, gravitational lensing, the bending of light by a massive object, can reveal the presence of a hidden black hole. But these methods have limits, and the most extreme black holes may remain beyond our ability to measure directly. The debate about the upper limit is not just about size. It also touches on fundamental questions about how the universe works. General relativity describes gravity on large scales, while quantum mechanics governs the behavior of matter and energy at very small scales. Black holes sit at the intersection of these two realms. At extreme masses, the effects of both theories become important. Some physicists think that new, undiscovered laws of physics may emerge under these conditions. For instance, a black hole approaching the upper limit might behave in ways that challenge our current models. It could reveal hidden aspects of space, time, or even hint at connections to theories like quantum gravity. Consider the analogy of a bridge built to hold a certain weight. As you add more weight, the bridge holds steady until one final load causes it to fail. In a similar way, space-time might handle the gravity of increasingly massive black holes up to a point. Beyond that, the structure could break down, leading to phenomena we cannot yet predict. This is why the 100 billion solar mass figure is so intriguing. It represents a theoretical boundary where something fundamental might change. Researchers continue to test these ideas using simulations and observations. Computer models allow them to recreate the conditions of galaxy clusters and track how black holes grow over billions of years. These simulations suggest that environmental factors, such as the availability of gas and the rate of galaxy mergers, play a major role in determining a black hole's final size. Observations of real galaxies help refine these models. Each time astronomers find a black hole heavier than expected, it challenges assumptions and pushes the limits of theory. It is possible that the true upper limit is higher or lower than the current estimate. It may vary depending on the environment or the history of the black hole. Some galaxies might support growth to extreme levels, while others naturally cap the size much earlier. Until we can observe a black hole near this boundary, the debate will continue. The discovery of Ton 618 and similar giants shows that the universe is capable of producing objects close to the theoretical threshold. Whether it can go beyond remains one of the most fascinating open questions in astrophysics. These colossal black holes are not just markers of scale. They are tests of our understanding of the cosmos. Silent experiments playing out on the largest stage imaginable. The largest black holes in the universe are more than silent cosmic monsters. They are engines of change that may have shaped the very structure of galaxies. These giants sit at the centers of galaxies, their gravity so strong that it influences stars, gas, and dark matter across vast distances. Over billions of years, they have played a key role in the evolution of the universe, regulating how galaxies grow and how stars form. Without them, the universe as we know it might look very different. At first glance, it may seem strange that a black hole, which swallows everything nearby, could have anything to do with building galaxies. But the relationship between a galaxy and its central black hole is complex. Galaxies form from enormous clouds of gas that collapse under gravity. As the gas condenses, stars begin to form, and clusters of stars merge into larger structures. In the middle of this process, matter also falls inward toward the center, feeding a growing black hole. The more massive the galaxy becomes, the more material is available to feed its central black hole. Over time, the two grow together, locked in a cycle of cause and effect. When a black hole feeds actively, the process releases tremendous energy. As gas and dust spiral toward the event horizon, they heat up and glow, creating an accretion disk. This disk can outshine the rest of the galaxy. In some cases, the energy output takes the form of powerful jets of particles that shoot outward at nearly the speed of light. These jets and the radiation from the accretion disk can push surrounding gas away from the center of the galaxy. By heating the gas and driving it outward, the black hole prevents it from cooling and collapsing into new stars. This process is called feedback, and it is one of the main ways black holes regulate star formation. Imagine a fire in a crowded room. The heat from the fire pushes people back, preventing them from moving closer. In the same way, the energy from an active black hole pushes gas away, creating a balance between inward collapse and outward force. If the black hole did not release this energy, the gas would continue to collapse unchecked, forming stars too quickly. The galaxy might grow rapidly but burn out just as fast, exhausting its fuel in a brief burst of activity. Feedback from the black hole helps slow this process, allowing the galaxy to grow in a more stable way over billions of years. Astronomers have found strong evidence for this connection. By studying many different galaxies, they discovered a clear relationship between the mass of a galaxy's central black hole and the properties of the galaxy itself, especially the speed at which stars move near the center. This suggests that the growth of the black hole and the growth of the galaxy are linked. Even though the black hole makes up only a tiny fraction of the galaxy's total mass, its influence extends far beyond its immediate surroundings. It acts like a regulator, keeping the galaxy's evolution in balance. The effects of a giant black hole can be seen on the scale of entire galaxy clusters. These clusters contain hundreds or even thousands of galaxies, along with vast clouds of hot gas. In some clusters, astronomers have observed huge cavities in the gas, created by jets from a central black hole. These cavities are so large they could contain multiple Milky Way face-sized galaxies. The energy required to carve out such structures is almost unimaginable. Yet it comes from matter falling into a single black hole at the cluster's center. This shows how a single object can influence an environment spanning millions of light years. The timing of this activity is important. In the early universe, when galaxies were young and full of gas, Black holes grew quickly. They fed on abundant material, releasing bursts of energy that shaped the galaxies forming around them. Many of the brightest quasars we see today come from this early era. These were times when black holes were at their most active, sculpting the structure of galaxies while they were still taking shape. Over time, as the available gas was consumed or expelled, black holes became quieter. Today, most large galaxies, including our own Milky Way, contain central black holes that are mostly dormant. Even in their quiet state, their past activity has left lasting effects on the surrounding stars and gas. Consider our galaxy as an example. Sagittarius A, the supermassive black hole at the Milky Way's center, is currently feeding at a very low rate. It produces only faint bursts of radiation, barely noticeable compared to active quasars. Yet the structure of the Milky Way suggests that in the past, Sagittarius A was more active. The central bulge of stars and the distribution of gas bear marks of past outflows, signs that the black hole once shaped its environment through feedback. Without this earlier activity, the Milky Way might have formed more stars at a faster pace, changing its appearance and possibly even affecting the development of planetary systems like our own. The relationship between black holes and star formation is a delicate balance. If a black hole is too quiet, gas flows freely to the center, creating rapid bursts of star formation. If it is too active, it can blow too much gas away, shutting down star formation entirely. This balance is why galaxies come in such a variety of shapes and sizes. Some are spiral galaxies like the Milky Way, with ongoing star formation in their disks. Others are elliptical galaxies, where star formation stopped long ago. In many cases, the differences can be traced back to how the central black hole interacted with its environment over time. Simulations of galaxy formation have confirmed that black holes are essential to explaining what we see in the universe today. When researchers run computer models without including the effects of black holes, galaxies grow too large and form stars too quickly. The results do not match the real universe. When they add black hole feedback to the simulations, the outcomes align more closely with observations. This suggests that the role of black holes is not just theoretical, but a fundamental part of cosmic history. The influence of a giant black hole is not limited to its host galaxy. By affecting the flow of gas within a galaxy cluster, it can influence the growth of other galaxies nearby. Jets from an active black hole can heat the cluster's gas, making it harder for that gas to cool and form new stars in other galaxies. In this way, a single black hole can shape the evolution of an entire group of galaxies, acting as a central engine that drives change on enormous scales. Imagine a tree in a forest dropping seeds into the soil. Some seeds take root and grow into new trees, while others are blocked by conditions in the environment. If a storm sweeps through and clears the soil, the pattern of growth changes for the entire forest. A black hole works in a similar way, influencing which regions of space are fertile for star formation and which are not. Its gravity and energy flows create the conditions that determine how galaxies grow. Over billions of years, these processes have built the large-scale structure of the universe. Galaxies and clusters are not scattered randomly. They form patterns shaped by both gravity and energy. The largest black holes, through their immense power, have helped create and maintain those patterns, though they are dark and silent now. Their past actions are written across the cosmos in the distribution of stars, the shape of galaxies, and the balance between light and darkness. Time behaves strangely near a black hole. The intense gravity around it does more than just pull on matter and light. It also stretches and slows the very flow of time itself. This effect, called time dilation, is a direct consequence of Einstein's theory of general relativity. In regions of extreme gravity, time moves differently than it does in places with weaker gravity. Near the edge of a black hole, time can slow almost to a stop compared to the rest of the universe. To an outside observer, anything approaching the black hole appears to move more and more slowly, as if caught in an endless pause. The boundary where no return is possible is called the event horizon. This is not a solid surface, but a point in space where escape becomes impossible even for light. As an object approaches this boundary, the effects of gravity grow stronger. To someone far away, watching from a safe distance, it looks like the object slows down as it gets closer to the event horizon. Its motions become stretched out in time. Light leaving the object also stretches, shifting to longer, redder wavelengths. This is why astronomers call the effect gravitational redshift. Eventually, from the distant observer's perspective, the object never quite crosses the horizon. Instead, it fades slowly into darkness, its final moments stretched out infinitely. For the object itself, the experience would be very different. If you were falling into a black hole, you would not notice your own time slowing down to you. Everything would feel normal. Your heartbeat, your thoughts, and the ticking of your watch would continue as usual. It is the outside universe that would seem to speed up. From your perspective, the rest of the cosmos would rush forward. Stars would appear to move faster, and distant events would unfold rapidly, as if someone had pressed fast forward on the universe. This strange reversal happens because time flows differently for each observer, depending on their position in the gravitational field. So picture this. Imagine standing on a hill while a friend stands in the valley below. If you shout to each other, the sound waves travel normally, but gravity affects how you experience time. For the person at the bottom of the valley where gravity is stronger, time moves a little more slowly than for the person at the top. In everyday life, this difference is so tiny that it does not matter. But near a black hole, where gravity is unimaginably strong, the difference becomes enormous. The valley in this example is like the space near the event horizon. The hill is like the rest of the universe. The closer you are to the black hole, the slower your clock runs compared to someone far away. Imagine one astronaut stays far from the black hole while the other descends toward it. The astronaut who stays back watches as their partner approaches the event horizon. From this viewpoint, the descending astronaut moves more and more slowly, their actions stretched out like a film played in slow motion. Eventually, they seem to freeze right at the edge, never crossing over. Their light becomes so redshifted that it fades from view completely. To the falling astronaut, however, nothing unusual happens. They see themselves falling normally and cross the horizon without noticing anything special. If they could look back, they would see the distant astronaut's clock racing ahead, ticking faster and faster. This distortion of time has been confirmed through experiments, though on much smaller scales. On Earth, scientists have measured time dilation using extremely precise atomic clocks. Clocks placed on airplanes, satellites, or even at different altitudes on a mountain tick at slightly different rates due to changes in gravity. The difference is tiny, just fractions of a second, but it matches the predictions of relativity. These tests give us confidence that the extreme effects near a black hole are real, even if we cannot experience them directly. The slowing of time near a black hole has fascinating consequences. If a spacecraft could orbit very close to the event horizon without falling in, time for the crew would pass much more slowly than for people far away. A single hour near the black hole might equal years or even centuries in the rest of the universe. This idea was famously explored in the film Interstellar, where astronauts visiting a planet near a black hole experienced only a few hours while decades passed elsewhere. The science behind this scenario is grounded in real physics, though the exact numbers depend on the black hole's mass and how close you are to it. The stronger the gravity, the greater the time distortion. Near smaller black holes, the effect is even more dramatic, because the gravitational pull changes sharply over short distances. Supermassive black holes, despite their immense gravity, have gentler slopes near the event horizon. This means an object could get very close without being torn apart by tidal forces. For this reason, supermassive black holes are the best places to imagine extreme time dilation occurring without immediate destruction. A stellar black hole, by contrast, would tear anything apart long before it reached the event horizon. From the perspective of the wider universe, black holes act like natural time machines. They allow us to see events in slow motion. When astronomers watch matter falling toward a black hole, they are not seeing it in real time. The light they detect has been stretched and delayed by the intense gravity. This means black holes offer a unique window into the behavior of matter under extreme conditions. In a sense, they let us peer at the very edge of time itself. The slowing of time also affects how we think about the fate of objects that fall into a black hole. From the outside, it appears as if nothing ever truly crosses the horizon. The object just fades, frozen in place forever. But from the object's own viewpoint, it crosses the horizon and continues inward. These two perspectives are both correct within their own frames of reference. This dual reality is a fundamental feature of relativity, and one of the reasons black holes are so challenging to fully understand. Consider what this means for the universe as a whole. A black hole could serve as a kind of cosmic record keeper. Light from material near the horizon takes longer and longer to escape, stretched across time until it becomes undetectable in a way. The black hole preserves a snapshot of everything that has ever fallen toward it, though that information is hidden from us. This leads to deep questions about whether information is truly lost inside a black hole, or whether it remains encoded somehow on the event horizon itself. Physicists continue to debate this problem, known as the black hole information paradox. The idea that time slows near a black hole reminds us that our experience of time is not universal. What feels steady and unchanging to us can vary dramatically elsewhere. On Earth, time differences caused by gravity are tiny. Near a black hole, they become overwhelming. This has practical effects as well. Satellites in orbit must account for small amounts of time dilation to provide accurate GPS signals. Without these corrections, navigation systems would quickly become inaccurate. This everyday example shows how relativity is not just a theory, but a real part of how the universe works. Black holes reveal the extreme end of this reality. Near their edges, time is stretched almost beyond recognition. From far away, events seem to freeze and fade. From up close, the rest of the cosmos races ahead. These two views exist side by side, shaped by the warping of space and time itself. Through them, black holes show us that time is not fixed. It is flexible, responsive to gravity, and deeply connected to the fabric of the universe. Black holes are often described as places where everything disappears. But when they are active, they can be the most powerful sources of energy in the universe. A black hole itself does not create light or heat. It is completely dark, a region from which nothing can escape. The energy we see comes from the matter falling toward it. As gas, dust, and even whole stars spiral inward, they form a disk around the black hole called an accretion disk. In this disk, particles collide at incredible speeds. Friction and compression heat the material to temperatures so high that it glows brightly across many wavelengths, from visible light to X-rays. The closer the matter gets to the event horizon, the hotter and more energetic it becomes. When the black hole is very massive and the feeding process is steady, the energy released can be enormous. In the most extreme cases, this energy output creates a quasar. A quasar is not a single object, but rather a galaxy with an active supermassive black hole at its center. The light from the accretion disk and its surrounding regions can outshine the combined light of every star in the host galaxy. This means that a relatively small region at the galaxy's core can be brighter than billions of stars spread across hundreds of thousands of light years to understand the scale. Imagine our Milky Way galaxy. It contains between 100 and 400 billion stars. Each star, including our Sun, produces its own light. Now picture all of that light combined into one blaze of brightness. A quasar's central black hole can match or exceed that level of output on its own. From Earth, a quasar billions of light years away can still be visible because of its intensity. Some of the most distant objects ever detected are quasars, their light having travelled across most of the age of the universe to reach us. The process that powers a quasar is extremely efficient compared to other sources of energy. When matter falls into a black hole, up to 10% of its mass can be converted directly into energy. For comparison, nuclear fusion in stars, like the reactions that power our Sun, converts less than 1% of mass into energy. This means that pound for pound, accretion onto a black hole produces far more energy than any natural process we know. A small amount of material falling into a black hole can release more energy than millions of nuclear bombs exploding at once. The radiation from a quasar does not simply shine outward like a light bulb. It interacts with the surrounding galaxy. Powerful winds and jets form as some of the material is funneled along magnetic fields and blasted away at nearly the speed of light. These jets can extend far beyond the galaxy itself, reaching distances of millions of light years as they move through space. They push and heat intergalactic gas. This activity has a profound effect on how the galaxy evolves. By expelling gas, the black hole prevents it from cooling and forming new stars. In this way, the black hole regulates the growth of its galaxy, acting as both a destroyer and a caretaker. One of the most famous examples of a powerful active black hole is the quasar TUN 618. It contains a black hole estimated to be about 66 billion times the mass of our Sun. The light from this quasar has travelled over 10 billion years to reach us, meaning we see it as it was when the universe was young. Even from that incredible distance, TUN 618 is bright enough for our instruments to study. The energy it produces comes entirely from material falling into its central black hole. This single object has a power output greater than entire clusters of galaxies combined. Closer to home, the black hole at the center of our Milky Way, Sagittarius A, is currently quiet. It consumes very little material and produces only weak bursts of radiation. However, evidence suggests that in the past it was much more active. Structures in the surrounding region, such as the Fermi bubbles, vast outflows of gas and energy, indicate that Sagittarius A once released powerful jets similar to those seen in quasars. If it became active again, the center of our galaxy would light up dramatically, possibly visible from across the universe. The difference between an active and inactive black hole comes down to fuel. A black hole needs a steady supply of gas and dust to maintain a bright accretion disk. In young galaxies, where gas is plentiful, black holes often feed at high rates. This is why the early universe contained so many quasars. Over time, as the galaxy consumes or expels its gas, the black hole has less to feed on. It becomes dormant, its glow fading until it is nearly invisible. Even the most massive black hole will remain dark if no matter falls into it. The energy potential is still there, but without fuel, it cannot be released. The light from a quasar is so strong that it can travel across billions of light years. This makes quasars important tools for studying the distant universe. By examining their spectra, astronomers can learn about the conditions of the early cosmos. The light passes through clouds of gas on its journey to Earth, and those clouds leave fingerprints in the form of absorption lines. These fingerprints reveal the composition and structure of matter that would otherwise be too far away to study. In this way, Black holes not only shape their own galaxies, but also help us understand the larger universe. The power of a quasar also comes with limits. If a black hole feeds too quickly, the intense radiation it produces can push back on the inflowing gas. This creates a balance point known as the Eddington limit, when the outward pressure of radiation equals the inward pull of gravity. The black hole cannot easily grow larger. In reality, some black holes may briefly exceed this limit, creating bursts of activity before settling back down. This feedback loop keeps the growth of the black hole and the surrounding galaxy in check. Imagine a small fire in a fireplace. If you add wood slowly, the fire burns steadily, producing heat without overwhelming the room. If you dump too much fuel on it at once, the fire flares up violently and may even push flames outward, burning the surrounding area. A black hole feeding on gas works the same way. A controlled flow allows steady growth, while too much fuel at once creates powerful outflows that push material away. This process prevents the galaxy from collapsing inward and burning out too quickly. The energy released by an active black hole is among the most extreme phenomena we can observe. Entire galaxies can be shaped by a single source of radiation and jets at their core. Over cosmic time, these outbursts have determined which galaxies continue forming stars and which fade into quiet collections of ancient stars. They have also influenced the distribution of gas between galaxies, affecting how new galaxies form. In this way, black holes act as regulators of the universe's structure. Even though the black hole itself is hidden, the effects of its energy are visible on vast scales. Radio images show jets stretching far into space. X-ray observations reveal hot gas, shaped by past eruptions. Optical telescopes capture the brilliant glow of the accretion disk. Together, these observations paint a picture of a process both violent and beautiful. A single black hole, fed by matter spiraling inward, can create a beacon visible across the universe. This beacon, a quasar, is a reminder that even in the darkest corners of space, energy can be released on a scale beyond anything else we know. The universe may hide its greatest giants in the simplest way possible, by showing us nothing at all. A black hole is by its nature invisible. It has no surface, no glow, no light to mark its presence. Even when its event horizon stretches across billions of kilometers, the black hole itself remains a perfect void. What we see are only the effects of what happens around it. Gas spiraling inward, stars being torn apart, jets of particles shooting into space. Without these signs, even the most massive black hole could sit in the center of our view, and we might never notice. This is the paradox of discovery. The largest black hole could be right in front of us, appearing as nothing more than a patch of empty sky. When astronomers search for black holes, they do not look for the black holes themselves. They look for movement and light. Stars near a black hole orbit under its immense gravity. Gas falling inward heats up and produces radiation. These are the fingerprints of a hidden object. By measuring the way nearby matter behaves, scientists can infer the mass and location of a black hole. This is how we know that our Milky Way has a supermassive black hole at its center. Astronomers tracked the orbits of stars over many years and found that they circled a point containing about 4 million times the mass of the Sunday. Nothing else could explain their motion. This method works well for nearby galaxies, but distance adds complexity. Farther away, individual stars blur together, and the subtle movements that reveal a black hole become impossible to track. If the black hole is also quiet, with no gas to feed on, it leaves behind almost no signal at all. The result is a region that appears unremarkable, a blank spot in an already dark sky from Earth. There would be no visible difference between a space filled with stars and one containing a black hole large enough to swallow entire solar systems. Consider the black hole known as Ton 618. It has a mass of around 66 billion suns and powers, a brilliant quasar. We can see it because material is falling into it, creating a glow so intense that it outshines its entire galaxy. If Ton 618 stopped feeding tomorrow, the light would fade. From our perspective, the quasar would vanish. The black hole would still be there, its gravity unchanged, but it would blend completely into the background. Without its glow, it would be as if it had never existed. The same is true for countless other black holes across the universe. Their visibility depends entirely on whether they are active. This creates a strange possibility. The most massive black hole ever to form might be one we never detect. It could sit at the center of a galaxy cluster, surrounded by stars and dark matter, yet appear invisible because it has no material falling into it. The cluster itself may look ordinary, just another collection of galaxies scattered across space. Only the subtle gravitational influence on the surrounding galaxies would hint at something extraordinary. But that signal might be so faint and spread out that we cannot measure it clearly. In this way, the universe could hide its greatest monster in plain sight. Imagine walking through a foggy landscape at night. Bright lights are easy to spot, but a deep lake without reflections appears as just another patch of darkness. You could stand at its edge without realizing it. A dormant black hole works the same way. If there is no glow to mark it, you see only the background stars. The void itself is invisible, even when it is unimaginably vast. The larger the black hole, the easier it is for it to hide. Its event horizon could encompass entire star systems, yet from a distance, it would look like nothing at all. Astronomers face this challenge every day. They build powerful telescopes to peer deeper into space, but they depend on light. Light tells us where to look and what to study. A black hole without light forces scientists to rely on indirect methods. Gravitational lensing is one such method. When a massive object bends the light of more distant objects, it creates distortions like arcs or rings. By studying these patterns, astronomers can map the distribution of mass in a region. A hidden black hole can reveal itself this way, but the effect is subtle. It requires careful observation and precise calculations. If the black hole is very far away, the signal can be lost amid the noise of the universe. Gravitational waves offer another clue. When two black holes collide, they send ripples through space itself. Instruments like LIGO and Virgo can detect these ripples. A collision involving an ultramassive black hole would release waves so powerful that they could be felt across billions of light years. Yet these events are rare. A single black hole, isolated and quiet, would produce no waves. It would remain undetected unless another object disturbed it. The paradox becomes sharper when we consider scale. A small black hole, perhaps 10 times the mass of the Sunday, can be easier to find than a giant one. If it is part of a binary system, pulling matter from a companion star, it creates a bright X-ray signal that stands out even across great distances. A massive black hole, by contrast, may consume matter so smoothly and quietly that it produces almost no radiation. It is like comparing a single loud shout to the steady silence of a deep ocean. The shout travels far and is easy to hear. The silence is harder to detect because there is nothing to grasp. This paradox also affects how we think about discovery. We often imagine that the largest or most dramatic objects will be the easiest to find in everyday life. A mountain is easier to see than a pebble. In space, the opposite can be true. A small but active black hole can be visible from across the universe, while a massive dormant one remains hidden. This reverses our expectations and challenges the way we search for cosmic structures. There may even be black holes hiding in data we already have. Large-scale sky surveys collect immense amounts of information. Within that data, patterns could exist that we have not yet recognized. A region that looks like empty space might contain subtle distortions caused by a black hole's gravity. As our tools and methods improve, we may find that some of these blank areas hold surprises. The act of discovery might not involve pointing a new telescope at the sky, but reinterpreting what we already see. Consider the galaxy cluster Abell 85, which contains one of the largest measured black holes, with a mass around 40 billion suns. The galaxy itself is dim and diffuse, a shadow of its former self. Its central black hole is mostly dormant. Only by studying the motion of stars and gas in great detail were astronomers able to infer its presence. From a distance, the cluster looks ordinary. Without careful analysis, the black hole would remain hidden forever. It is possible that other clusters contain even larger black holes, still waiting to be recognized. The paradox of discovery highlights how much we depend on contrast. We see stars because they shine against the darkness of space. We see galaxies because their combined light forms patterns. A black hole disrupts this balance. It does not shine, it does not reflect. It removes light and leaves nothing in its place. The more perfect its darkness, the harder it is to notice. The largest black hole may not need to hide. It may simply exist, silent and unseen. In the center of a region we have already mapped. We might have looked directly at it without realizing it was there, mistaking its immense presence for empty space. The universe is vast beyond comprehension, and in that immensity there may exist black holes so large that we will never truly find them. Black holes are already difficult to detect, even when they are nearby and active. They produce no light of their own, and we only see them by watching how they affect surrounding matter. A black hole that feeds on gas or stars can reveal itself through the radiation given off by the material as it falls inward. But if there is no fuel to consume, a black hole becomes completely silent. It blends into the darkness of space, leaving only gravity as its trace. For the most massive black holes, this silence, combined with extreme distance, could mean that they remain permanently hidden from us, their existence known only through theory and indirect evidence. Even the black holes we have already found push the limits of our instruments. Ton 618, one of the largest ever measured, has a mass of about 66 billion suns. Its size is almost impossible to picture. If it sat at the center of our solar system, its event horizon would stretch far beyond Pluto and deep into the outer regions of the Kuiper Belt. It shines brightly only because material is actively falling into it, creating a blazing quasar visible across billions of light. Years without this constant feeding, Ton 618 would vanish from sight. The same object would go from one of the brightest beacons in the universe to total invisibility. It would still be there, unchanged, but we would have no way to see it. This shows the central problem in detecting the largest black holes. Their visibility depends on activity. In the early universe, when galaxies were young and full of gas, black holes had abundant material to consume. Many were active, producing powerful jets and glowing accretion disks. These early black holes shaped the galaxies around them and lit up the cosmos as quasars. Over time, as the gas supply dwindled, many of these giants went quiet. Today, a massive black hole at the center of a galaxy might sit in complete darkness. With no glow to mark it, the galaxy could look like any other. The black hole would be nothing more than an unseen weight holding the galaxy together. Distance adds another layer of difficulty. The farther away an object is, the fainter its signals become. Light takes time to travel, and the universe is expanding, stretching that light as it moves through space. For black holes at extreme distances, their signals may be stretched so much that they fall outside the range of our detectors. Even if the black hole is active, its light could arrive so faint and distorted that we cannot separate it from the background. Beyond a certain point, the expansion of the universe pushes objects away from us faster than their light can travel. Anything beyond that cosmic horizon is permanently hidden. If the largest black hole lies beyond that limit, we will never see it, no matter how advanced our technology becomes. Some black holes may also be hidden by their environment. The centers of galaxy clusters are chaotic regions filled with stars, gas, and dark matter. A black hole sitting at the heart of such a cluster could be surrounded by clouds of material that block our view. Even if it produces some light, it might be absorbed or scattered before reaching us. We would only see the effects of its gravity, such as the motion of nearby galaxies or distortions in the light of background objects caused by gravitational lensing. These indirect signs can suggest the presence of something massive, but they cannot reveal the black hole itself. Without direct observation, its true size and nature remain uncertain. Gravitational waves offer another way to detect black holes, but they have their own limits. When two black holes merge, they create ripples in the fabric of space. Instruments on Earth can detect these waves if they are strong enough and close enough. A collision involving a truly enormous black hole would produce powerful waves, but these events are rare. If the largest black hole in the universe is isolated, never merging with another, it would create no such signal. It would remain completely silent, invisible even to the detectors designed to sense the unseen. Imagine standing on a shore at night, looking across an endless ocean. You see the lights of nearby ships and distant lighthouses, but beyond a certain distance there is only darkness. You know there are ships out there sailing in the unseen waters, but their lights cannot reach you. Space works the same way. The black holes we know are like the visible ships, their activity bright enough to be detected. The ones beyond our reach are like the ships lost in the night, present but forever unseen. The largest black hole of all could be one of these, too far and too quiet for its signal to ever arrive. Even if such a black hole were closer, its behavior could still keep it hidden. A black hole does not need to produce much radiation to grow. It can consume stars and gas in a smooth, steady flow that releases very little energy. The larger the black hole, the easier it is for matter to fall inward, without creating bright flares. This quiet feeding makes it harder to detect. From a distance, the galaxy hosting such a black hole might look ordinary. Its central region no different from any other. The black hole would be the ultimate hidden presence, shaping its surroundings without leaving a visible mark. Astronomers face the paradox that the very traits making a black hole massive also make it difficult to find. A black hole becomes enormous by consuming vast amounts of matter over billions of years. But as it grows, it can also clear out its own environment. The energy released during its active phases pushes gas away, cutting off the supply of fuel. When the feeding slows, the glow fades, leaving the black hole dormant. In this state, it is both more massive and more invisible than before. By the time it reaches its full size, it may have erased nearly every clue that could reveal it. We can use theory and simulation to explore these possibilities. Computer models allow scientists to track how black holes and galaxies evolve together. These models suggest that in the densest regions of the early universe, black holes could grow to tens of billions of solar masses or more. Under rare conditions, one might even reach 100 billion solar masses. But the models also show that such growth would be accompanied by violent feedback, blasting away surrounding gas and slowing further feeding. This creates a natural limit on how large a black hole can become. Whether the universe has ever produced one at this extreme edge remains unknown. The only evidence we might ever have for the largest black hole could come from its gravitational effects on a cosmic scale. If it sits at the center of a galaxy cluster, its presence might be inferred from the way galaxies move around it or from the bending of light passing nearby. These signs would tell us that something extraordinary is there, but not exactly what it is. It would be like seeing a shadow move across a curtain without knowing what cast it. The true size and nature of the object would remain hidden behind the veil. It is possible that we have already observed regions influenced by such a black hole without realizing it. In the maps of the universe created by large sky surveys, there are countless points of darkness where little light reaches us. Some of these gaps are simply empty space. Others may hide entire clusters of galaxies. Within those clusters, there could be a single black hole so massive that it rules its surroundings, yet leaves no direct trace. Without a glowing accretion disk or a dramatic merger, it remains a silent ruler, a mystery we can only imagine. The universe does not promise to reveal all of its secrets. Some black holes are close enough and active enough for us to study in detail. Others sit far beyond our reach, their signals too weak or too faint to ever detect. The largest black hole may belong to this second group. It may exist right now, shaping the motion of stars and galaxies on scales we can barely comprehend. Yet for us, it would be nothing more than a theory supported by indirect hints, a presence known through its absence, forever beyond the reach of direct discovery.